Good boy. Good boy. Let's see, this looks good. This looks good. Test 1 2 3. Test. Test 1 2 3. Okay, that looks good. I saw Castle in the Sky Nightcore on there. Let's see how this is. Okay. Gotta close all the 3 blue, 1 brown. All right. Oh, that's new. No, that's not new. Man, it's really snowing. Okay. I think I'm 2 back. Oh, it's been a while. Yeah, I haven't been streaming. Damn, I didn't get Q4 on this? Still ranked 944, so it must not have been too easy. Maximum score from grid operations. I just didn't even do it. I didn't even finish it. Based on max and max 3, I'm going to guess that I came up with a solution and it was too slow. Did you peek and skip? No. I like, this is all virtuals. Pretty good though. I don't know, but like, it's been what? Saturday, March, wait, what? I'm confused. Oh, no. Okay, no, these are not virtuals. These are actually like real. Let's see. Here we go. These are the virtuals. Which, not too bad. I don't know. Why does it show O out of 4 on the last reel? I don't know. Oh, is that why you said, did I peek and skip? Maybe I did. Or maybe I signed up. Let's see. August 2nd would have been... Probably what happened is this. Oh no, this is a bi-weekly though. No, yeah, probably what happened was I was like hanging out with my girlfriend at the time, and she wound up staying the night. So I like registered maybe and then like didn't do it. I guess I don't know. Or no, maybe this was unranked. Maybe this was like they like undid it or something like that. I don't know. Okay. But that shows me, I think I'm up to here. So I'll just go for it. Or maybe I didn't get any of them. I don't know. It's been a minute, so. Reverse the letters, then special characters in a string. Reverse the lowercase letters and place them back in the positions originally occupied by the letters. Reverse, and what? Okay. Reverse the special characters and place them back in positions originally occupied by special characters. So. Is there anything other than letters and special characters? Only of lowercase English letters and special characters. So why would you not just reverse S, right? Am I crazy? No, you wouldn't just reverse S. It needs to be, okay. So I'll say A is if C in ASCII lowercase. Okay, B is that. Whatever, that's fine. B dot reverse res is this. Turn that dot join res for I in range length S. If S at I in ASCII lowercase. And I'll say J and K are 0 and 0. Res dot append A at J. Else res dot append A at K. K plus equals 1. Right, that should be okay. Uh-oh. So for this one, it flips out. So it should, let's see, at 0, at 0. Oh, B at K, not A at K. Okay, we got something that looks fine. That looks fine. All right, good enough. Minimum K to reduce array with a limit. You're given a positive integer array nums. For a positive integer K, to find non-positive nums in K is the minimum number of operations needed to make every element of nums non-positive by reducing it by K. So non-positive is probably including 0. On the ABC this morning, I got TLE for 2 test cases on E. I got 9 TLE trying to optimize. Then when I finally found a way to optimize it enough, I could only AC 33 seconds after the end of the contest. Oh, that sucks. That's for @coder ABC? That's rough. What am I doing? The minimum value of K. All right, well, I guess you could binary search, right? Is there an easier way to do that? You would just be like %K round up, and then you try all of them. I'm guessing nums has to be positive. So in that case, 0 will never work. So I'll say range from 1 to, I guess, oh wait, the minimum value of K such that non-positive of nums in K is less than or equal to K squared. I don't know if that's monotonic. I need to kind of tell myself that that's monotonic. Ten to the fifth. Let's see. If K was equal to the maximum element in nums, then I still don't think that would even be the case, right? Like, if nums was like, if K was 100, every element you could okay, for a positive integer K to find non-positive nums K, is the minimum number of operations needed to make every element of nums non-positive. In one operation, you can choose an index I and reduce nums at I by K. So, okay. Let's say n is 1e5, and every element in nums is 1. So therefore, you need 1e5 operations, right? So you need at least the square root of that. Well, no, it's still monotonic though, for sure. Because like, the larger the number you choose, the more operations you can perform and the less operations you need to perform. So the fact that one of them is linear, this is linear, and this is non-linear actually just happens to not matter. If it was like these were subtracted, then it would start to matter, but they're added together. So we'll do that. We'll say max A. Check K. It's going to be this, probably +1, because this is going to return the insertion order, but it's arranged starting at 1, so index 0 actually corresponds to element 1. Okay, let's see. For I in range n, that's fine. For I in range n, cur is 0, return cur is less than or equal to k times k. Cur plus equals, it's going to be something like, let's see, if it's something over k, it's over k plus 1, right? Let's say k is equal to 5. That means if you have 6, you need to do it twice. 7, 8, 9, same. 10, you need to do it twice. 11, you need to do it 3 times. So it's over k rounded up, right? So it should be plus k minus 1 over k. Is that math right? 6 plus k minus 1 is going to be 10. This is going to be the first element where you need 2. If you had 5, you would only need 1. Yeah. Shit. What does this mean? Bisect left missing additional requirement. Oh, I need the actual, like, what am I searching for? I'm searching for the first element that works. That seems right. I'm not going to overthink it. 3, 1. Maybe I should have overthought it. Okay, what happened here? So it should have said cur at 1. Damn. All right, fair enough. So it's not just max of A. You know what? Whatever. We're just going to do that. Damn, if that was the only thing, that's like, that sucks. They got almost every test case. That one stings. That's pretty bad. Longest strictly increasing subsequence of non-zero bitwise and. Return the length of the longest strictly increasing subsequence in nums whose bitwise and is non-zero. If no such subsequence exists, return 0. Well, this seems like one of those things where you just take every bit. You just say, like, what's the longest increasing subsequence among everything that has a ones bit? Right? And then you're just like, because you know all of the elements in your longest increasing subsequence are going to at least have 1 bit in common. That's like the definition of a non-zero bitwise and. So just separate them all out by what bits they have, and then go from there. How big can these numbers be? 10 to the 9? 2 to the 20, not quite big enough. 2 to the 24. 1, 2, 3, 1, 2, 3, not quite big enough. Whatever, we'll just do 32. So I'll say, I'm going to keep this as nums. A is, no, I'm going to call this B is that for blank in range 32. For IX and enumerate nums. Bit equals, how do I want to do this? 2 to the 10 is slightly larger than 10 to the third. Yeah, it's the right way to think about it. Bit is equal to, I just haven't done like Codeforces or Leetcode or anything in quite a while. Like, let's see, let's look at my heat map here. Yeah, it's been like 3 weeks. And I was kind of on a roll there. I was doing some like master level problems, grandmaster. This is, I think, the hardest problem I've ever done on Codeforces. And the last one. Maybe ever. Okay, bit is, I don't know, 0, right? Or no, this is the issue, is I haven't done like Python in quite a while. For bit in range 32, if 1 to the bit and x, that means that this does contain that. So b at bit dot append x. Okay, now we have them all sorted. So then I can just say something that's like, was it as hard as you expected? What was the deal with this one? Oh, no, I'm thinking of a different one. I don't know, I'll let it load. B at bit.append x. Okay, and then I just need something that's like return max of lis at b at I for I in range 32. And then I just need to have like, this is the longest increasing subsequence in the ath array. And then I need to refresh myself on how longest increasing subsequence works. So no, it's not that bad. This music's a little distracting though. There we go. A little calmer, I guess. Oh, thank you, Kemend, for following. Okay, so LIS isn't that bad. It's just something that's like, res is that, and then we're going to return the length of the longest one we found. So for x in A, I is res dot, it's not longest, it's longest strictly increasing. So I want bisect right, no, bisect left A and X if I is equal to length of, not A, res and X. If it's equal to length of res, this is more distracting. If I is equal to length of res dot append X, else res at I equals X. I think it's something like this, right? This sounds right. Let's take a look. Whoops. Wrong language. Int is not iterable, fair enough. LIS of B at I for I in range 32. I think it's probably just, I need to like grab that, yeah. Uh-oh. A is a generator expression? That should not be the case at all. And also res should not contain this weird thing here. So res is that. Oh, that was probably the problem before too. Okay, it says 5.7, 5.7, 5.4.7, it says 4.7. That all looks right. I'm pretty confident this is what longest increasing subsequence is. I guess I just want to check, like, if I said 5.5.4.7, is it going to say that's 3 here? Is it going to say, like, okay, you have 5.5.7. No, it's smart enough to be like, I think if I said bisect right here, then it would be longest non-decreasing. Yeah, so it's bisect left. Okay. Looks pretty good. 231, 231. Nice. Okay, it finally loaded. Query jungler. You're a jungler, the role, you want to hunt monsters in the jungle. Okay. Given the number of trees in the jungle, blah, blah, blah. You're going to find a minimum integer k such that there exists k paths to satisfy the following conditions. Each path must start at the root Every vertex with a monster must be included in at least one of these paths. A vertex is considered included in a path if it is one of the path's vertices, including endpoints. Yeah, this one was difficult. It's nice because I'm like, this felt within reach. There's been some problems on AppCoder where I'm like, fuck, how? Like, it didn't rely on something I don't know. I just wouldn't be able to figure that out. This one felt like I can figure that out. Like, there's a world where I practiced enough and I could actually come up with a solution to this. It's just very tricky. But it's on the edge. Part of me was also like, fuck, that's so difficult. Give an integer array nums and an integer k. Your task is partition nums into exactly k subarrays and return an integer denoting the minimum possible score among all valid partitions. The score of a partition is the sum of the values of all its subarrays. The value of a subarray is defined as that. Okay, this seems like if you could query, did I solve it without hints? No, I didn't. I looked at the first hint and then I got it. Because usually that gives it away. The value of a subarray is defined as sumr times subr plus 1, sumr plus 1 over 2. Wait, okay. So the value of a subarray is the sum of all of its elements times the sum of all of its elements plus 1 over 2. That seems like a very random thing. But I guess what I can say is that that scales quadratically, right? So I guess it's monotonic, assuming there's no negative numbers. Even if there were negative numbers, it would still scale quadratically, right? Because like, and maybe there'd be some weird stuff around 1 and 0, but it doesn't matter. So the sum of values of all of its subarrays. So the hope would be that you would be able to just query a left and right and say, this has exactly this score. This partition has exactly this score. How big can K be? K can be, well, they can both be 1,000. So you could have a DP state space that's like 1,000 by 1,000. So you could say, like, I have this many partitions left. I have this index that I'm at. Let's see where I can go from there. But I think a difficult thing would be that it's still not obvious how you would get that down from O of n cubed if like k equals n. Because you'd say, okay, dp at I at j is equal to at ith index with j partitions. Something like this. And we're trying to optimize that, right? Like have the highest score, the lowest score. Okay. This feels like this is just such an arbitrary thing. This feels like they made this with the intent for some algebra to be done. That's like that's the impression I get. Like it feels almost like you could. So then the problem though is like, okay, this is kind of O of n squared. But then your transition, you need a way to have this be O of 1 in this case, or you would need a way to have this be O of n and this be O of n. The thing is, like, this seems like you would say, like, draw new partition, which would be O of n. So that's not good enough. Well, I guess let's just see what happens. So you have two things here. If you said, it might even be a weird like binary search thing again, but okay, let's see. So if you said 5 and 1, and then you added in 2, I don't think there's any way to do that in O of 1, because that would have required keeping track of what this array was, right? Sum of subarrays times sum of Because if you add in the 2, you need to know how many times that appeared. If you even had that information, would that help you? Because there's a world where you say, like, if it scales quadratically, you would want to minimize the maximum. If you minimize the maximum sum, like, I guess what I'm thinking about is if you had like 1, 2, 3, 4, and then you could put 5 into here or here. Is there ever any world where like this is greater than this and you want to put it in this one? Because 5, if I'm reading this right, sum of the subarray times sum of the subarray plus 1 over 2. If you put it in here, how much does that impact your score? You're saying, now I've added in 5 times 6 over 2 is 15. So I've added in 15 plus 9 times 10 over 2 is 45 plus something bigger plus something bigger plus something bigger. Or I've added in something here. I feel like this is going to have to do with convexity. And maybe it's the slope trick. If it's the slope trick, I'm in trouble. That's pretty rough in that case, but... What's the slope trick? The slope trick is like, it shows up on like, I'd say 2200 and higher rated problems in Codeforces at least. It's the idea that if you have some, I think the base case people use a lot is if you have something that's like dp at j is equal to dp at I plus, let's say like dp at I is less than j, like you're at some previous dp at I plus a at I plus j minus I. So you're kind of like, okay, there's some, or let's say a at j, there's some like, or no, a at I is fine. Basically, it's like this idea that there's some affine relationship between dp at I and dp at j. The problem is it feels irreducible. It feels like there's no way to do this not in O of n cubed, or I guess O of n squared, where you say for every dp at j, try every previous dp at I, because there's this pretty non-trivial like relationship between, or no, I think this should be a at j, it's fine. Like there's this pretty non-trivial relationship between each index. So it feels like, well, how could you possibly, let me pull this up here. So if this is dp at j, and this is some previous dp at I, and you have some relationship, like, and you need to look for like, okay, well, what's the best one I could have had? Let's say, something like that. But these are like, these follow a pretty specific, I guess, recurrence relation. So you're here and you're like, this is going to have some cost, and this is going to have some cost, and this is going to have some cost, and you want to find like, let's say the minimum one or something like that. Yeah, or the maximum, whatever. And then you need to know in not O of n squared, you need to know in O of n, aha, it's exactly this one. Like this is the right answer. And the question is like, how could you possibly do that? But the idea is if your recurrence relation Or your, yeah, I guess your, is that the right way to put it? Yeah, your recurrence relation. CHT. What is that? If it's affine, then that means you're going to have something that's like dp at j is equal to m times dp at I plus b, right? Yeah, it's the convex hull trick. In case anyone else is watching, the idea is that you say, okay, dp at j, or paying attention to this, if you have this kind of specific way that you can set up your recurrence relation or your DP formulation, then you can say, okay, well, I don't want to test each of these individually. What I want to do is like say some DP at I is going to just go up like that, and they're going to have all these slopes. But then the moment I know that this slope is just higher than this slope and the number is higher than that number, then like I never care about this again. So that's not going to be relevant. And if there's some number here that's like this, then there's going to be some later point where that is the slope that I care about and this slope no longer matters. So in a way, it's like you only really have to keep track of like a finite number of slopes. I mean, it's always finite, but you only have to keep track of like, you can reduce this complexity down so that it doesn't dominate, and you no longer have O of n squared, you have O of n. I hope that's not what this is. But perhaps I'm overthinking it. I mean, we do have O of n squared available, so. The other option I guess I'm thinking about is that you could reduce it so that you could say, do I start a new partition here, or do I add this to the previous partition? If you could formulate it so that that was your transition, then that's O of 1 and you'd be fine. But I would need a way to say here, like, if this was my previous, like, I would need a way to say, like, this was my previous thing. But I don't see how you could just add that in. Unless you binary searched, I guess. No, that doesn't really mean anything. Well, let me just do some algebra here. So the score of A is equal to I guess I'll say f of B, where B is all the subarrays in A. Okay. And then, or no, that's not the score. What do they call this? That's the score, and then the value of B is equal to sum of B times sum of B plus 1 over 2. So I guess if you're dividing everything in here, and this is the sum of scores, the sum of values, if you're taking a sum of everything, you could just say, okay, well, forget this. Just take score of A over 2. Okay, take that out. So now we've reformulated it so that f of B is equal to sum of B times sum of B plus 1. For degree 2. Okay, but there it seems that we would have a bunch of parabolas instead of lines. That's a good question. I wonder if you could do, I wonder if you could do that with parabolas. I don't know. Yeah, because I guess the question is like here you've kind of reduced it, if my memory serves me, to a monotonic stack that you can kind of operate in O of 1. Then the question would become like, okay, if there was some mono stack, and this gets you, I think, yeah, convex hole trick is the more common way people talk about it. If that gets you that, what thing would get you, I guess, like a 2D convex hole trick? I don't know. Yeah. Okay, but sum of b times sum of b plus 1. Is there a way to, for each I, if fi of j is the cost of doing transition j minus I, each f of I must be affine, right? Yeah. Yeah, exactly. And I think the j minus I, where they say like plus the distance between the elements in the array, like that is an example of like a yeah, linear slope. So then I feel like a lot of the time that points to that trick as like what they want you to do. J2I. Oh. Cost of doing transition J to I. Yeah. And I think like J minus I is like the primary example people like to use. But yeah, I think there's other examples too. Where like as long as you just know that transition, I think it's each F, yeah, like as long as you know that transition is affine, you only need to keep track of J, like F, like the slope at how dp at J will transition into dp at I for each J, and then you can maintain the monotonic stack. But I'm getting ahead of myself because I'm having trouble with this problem here. Integer to the minimum possible score among all valid partitions. I'm going to keep with this for a second, and then I'm going to try to come up with a greedy formulation. Because I think if you could make a greedy formulation that says if moving 5 from here to here, like makes, if the sum here is greater than the sum here, you could move 5, something like that. I don't know. Maybe I'm overthinking it though. Like, I don't know. We do get O of n squared. So like in this example, you could just say, yeah, I feel like I'm overthinking this. I feel like with 900 solves especially, I don't know. Like, because, okay, we can get a couple things right off the bat. We can just get f of L and R is equal to score of A from L to R, right? We can just straight up get this information. And like if I can use this as a logical building block, like I don't think it's useful to think about this kind of stuff or like convex hole trick. This is like already a stepping stone. So how would you do this? How would you say get the score from L to R, take every single L to R, pre-calculate it. You'd say for L in range N, I could upsolve it with n cubed worst case complexity. Maybe others cheesed it. Oh. Wait, you could just do this in O of n cubed? Okay, damn. Okay, but if I get the score, then I appreciate you saying that because it's the exact kind of thing where I'm like, I wish someone would just tell me that before, because otherwise it's like fucking maddening to like, in my mind, get the obvious sign that, okay, they want you to do it in O of n squared at worst, maybe O of n squared log n. And then it's just straight up O of n cubed. Like, those are just the worst. And then you're going to have some sort of rolling sum, right? Where you say, I mean, I guess you could do it with like a segment tree or something weird, but that seems kind of like overkill. No, that's fine. You say, okay, score from L to R, and then you would say score from L to R is equal to all the values, and then every no, that's fine. You take a prefix sum, right? So the score, you're going to say for every... So we have the value that's like... sometimes sum plus 1 over 2. This seems kind of challenging enough that I think it's worth going. What's up, Urinator? Welcome. So we have value. And then we have score. Value we just pre-calculate. That's fine. We just say, okay, for every L, you're just going to have the sum for every R. So you just take every L, you take every R going forward. That's O of n squared to get that. And then for score, what you say is, okay, run a prefix sum on this. And then for every score, you would say, if you have some, let's move this down. If you have some L and R bounds you care about, then for every, this would be the prefix sum. This is the value according to the L starting location up to the R ending location. So you would say for every L starting location, take all of these, and then you would have like P sum or score, I guess, at R minus score at L minus 1. That's sloppy. Score at R minus score at I minus 1 for all I is less than or equal to, for all I in this range. So then you could get this in O of n squared as well, right? No, that's not O of n squared. That's still O of n cubed. Shit. Right? Unless you used a segment tree, and then you could do something weird with that, but... Wait, is it O of n cubed? Because here we're doing this two-pointer thing to get this down to O of n squared. Is there something similar we could do here? Or could we do a 2D prefix sum? Yeah, couldn't you just do a 2D prefix sum? Am I crazy? So you have some table. These are all the L. These are all the R. So if you have these points, you're saying like, I guess from L to L. And this would be from L to R, right? So you wouldn't want to do this because what this would entail is you would say every time you increment R, you need to like recalculate a whole new thing. And you can't really do that in one dimension because it's going to take O of R minus L to do. So if instead you just said like prefix of, you just have some function. You take a 2D prefix sum. Right? And what this would mean is, I'm actually going to get rid of this. It's not really relevant. I think this is fine. So prefix at I at j is going to be, what is this? Value. Value for a I up to a j, right? And then if you take a query, you're like all of the prefixes in this area, or all of the values in this area. And then it would be from L comma L, from like the first thing and itself, that single subarray, all the way up to L and R. No, all the way up to R and R. And then that's going to get you score L and R. The score for that subarray. Or for that partition. Okay. And then we get score in O of n squared. This feels like the right track. This feels sufficiently kind of challenging, but it's still not really clear to me where you go from there. This is where I'm kind of like, even if you took that for granted, it's not really obvious what you would do. So then we're saying you can get a score from L to R in O of 1, which is cool. Could you just cheese this with O of n cubed? That seems really lazy. Or I don't know about lazy, but that just seems like not feasible. That seems like there's going to be a lot of wrong answers. You know it's going to monotonically increase, at least. You also, I think you do know that the score is going to increase like super linearly. So I think from there you could binary search and say, just try to greedily, yeah, I'm going to try to prove the greedy formulation, because if I can prove that, then I'm good. So the optimal solution is min. I'm not trying to minimize the maximum or anything, right? But I think what I'm trying to show is that if you were trying to minimize the maximum, that would have the same effect on the greedy formulation as this is. Because minimizing the if I can prove that minimizing the maximum is optimal, then I'm golden. So return an integer denoting the minimum possible score among all valid partitions. Wait, I think I might be overthinking that. Exactly k subarrays, return an integer denoting the minimum possible score among all valid partitions. So here, one optimal solution is 5 and 1, 2, 1. So the first one has a subarray sum, a score of 5, or no, 15. The second one has a score of 1 plus 1 plus 3 plus 6 plus... Fuck. Yeah, that's pretty sure. So... Wait, am I... Oh my god, am I... Wait. Okay. Okay, I'm adding an extra step. They're not... Okay, I made this so much more complicated than it needs to be. I thought it was saying one partition... Where's my here? I thought it was saying this is a partition, and for this partition, you're finding for every single subarray in that, you're finding some quadratic form, like quadratic relationship there. I don't think that's what this is saying. I think this is saying if you have some, if you have something, oh no, oh I fucked it up. Sometimes Excalibur freaks out. Okay, if you have some array, a partition is just all of these, and then it's just the sum of squares of these, not the sum of squares of subarrays of these. Okay, that's a lot simpler then. Doesn't really matter. That actually was this whole thing. I kind of reduced that out, but whatever. It's basically the sum of squares of sums of subarrays, basically. Shit. Okay, well then I do think you can do something like this. I do think there's some sort of O of 1 transition then. Right? The score of a partition is the sum of the values of its subarrays. So here it's just saying 15. The sum here is 4. 4 times 5 over 2 is 10. So the total is 25. Oh, boy. Well, in that case, you know that you're going to have some sort of... Yeah, okay. So the optimal... the optimal solution is going to be something like x times x plus 1 plus, let's do x0, x1 times x1 plus 1 plus ... over 2. So this doesn't matter anymore. You just divide the ending result by 2. So we'll just deal with that. There we go. That's sufficiently menacing. So then you basically have a bunch of quadratically scaling things that you need to take a sum of, right? So the optimal solution is going to be something... Why do we divide by 2? I don't know. It says to divide by 2, so... Great. I assume it's because it's kind of trying to say, like, the nth... like, sum of natural numbers kind of a thing. Okay, so we're basically going to get something that's like y0 squared plus y1 squared. Right? It's kind of something like this. And I mean, maybe this is really lazy math, but I feel like you could just say, for some x0 times x0 plus 1, there's going to be some y0 between x0 and x0 plus 1 that it squared is going to be equal to this. Right? So like 1 times 2 is 2. So there's some number between 1 and 2, the square root of 2, that squared is going to be that. So I guess we kind of want like an addition. If I'm actually being pretty exact here, then I don't need to round. I can say where xi is less than or equal to yi is less than or equal to xi plus 1. So if we take another example, let's say like xi equals 5. Then in that world, 5 times 6 equals 30. According to what I'm saying, the square root of 30 should be between that. And almost just by going backwards through the same logic, that's how I would intuit that that's indeed the case. But let's see if that's true. Yeah, 5.5. Great. So now I have this formulation, and it feels very much not like a stretch to say to optimize this, you would want to distribute these as thinly as possible. So the greedy formulation is how do I put this? I want to make like an exchange argument, but the thing is there's kind of like a missing thing here in the exchange argument where I'm kind of saying, okay, just assume there's some binary search. Do I care about proving this to myself that much? What's my time? 38 minutes. Yeah, I'll take another like 2 minutes to think about this. So, and I'm going to save myself a wrong answer. Return res over 2. Okay, so the idea is if there was some yi that's too large, you would necessarily want to decrease it. Because you would rather have, so yeah, I'll say like if yi okay, this is what I'll say. Assume some threshold. So for all yi, you want it to be less than this threshold. And then if there's some yi that is greater than the threshold, then, wait, what is the binary search going to look like? It's going to say what's the minimum threshold. It's going to say what's the minimum number you can have where, no, but then even within that threshold, you're going to have weird problems, right? Are you? No, I don't think so. So if yi is greater than the threshold and yi plus 1 is, I guess, plus a at j is less than or equal to the threshold, then take a at j away from yi and put it into y at I plus 1. So it's like that like candy problem on Leetcode. I think that's fine. I believe that. So in that world, that was a colossal waste of time because the problem was way simpler than I thought it was. So there's going to be some sort of binary search. Res is bisect left. Okay, you want the smallest number that works. You could have a really big threshold where you say, I want the threshold to be 100. And then you'd say, okay, great. Well, everything summed together is less than or equal to 100. So you can fit the whole array into that if you wanted to. This is going to get me... I think what I want is to say, I'm going to say def calc something. And then there's going to be def check something. And this is with threshold, find min sum. Yeah, that's fine. And then this one is with threshold, find min k. Find max k. So then it's going to go down and down and down, and it's going to say, okay, if you tried 100, then that's fine. If you tried 50, that's fine. 25, that's fine. 12 and a half, that's fine. 6, though, then it's going to say, well, you could put this into a threshold of at most 6. And then this into a threshold of at most 6. And it would say, you're good. And then it would say, okay, can you do 4, 3? No. Can you do 5? Yes. You could say, group this in with 5. Group this in. I think I honestly want to just be like Leetcode minimum max of max partition. There's literally a problem that's already this. And it's called this problem that I'm doing. That's funny. Partition array, maximum sum, Leetcode minimum partition sum, something like that. Damn, I'm certain this is already minimize maximum products. No, I'm certain this is already a Leetcode problem. Whatever, I'll just code it out. So this is going to have check the threshold. It's going to be range from, I guess the threshold could be 0, and then you're fucked, right? What would that mean? That would mean it keeps making new subarrays every single time. I don't think I want to do it that way. I think I want like the minimum. It needs to be at least the maximum element in nums. Like there's no way you could partition this so that you're looking for a subarray sum of less than 5. So the min of A up to, I guess, the sum of A plus 1. Because if K was equal to 1, you would just say, all right, well, I want everything then. You're looking for the lowest threshold that will work. So the first one. Okay. J is equal to 0. This is subarrays so far. Cur is 0. Cur subarray sum. And then I think I just want like prefix equals, just get the prefix sum. Plus a 0 in the beginning so that it's easier to query. For I and X in enumerate A, is there any point to the cur? Yeah, that's fine. I actually don't need this then. Cur. Let's see, if cur plus X is greater than threshold, J plus equals 1, cur equals X. I'm going to set it up this way. Reset current and then add in X. And then return J is less than or equal to K. Can you do it in at least this many partitions? Okay, and then with this threshold, it's going to be really similar, except now I'm not keeping track of the number of subarrays I've seen. I'm returning the score. And I think right here I would want to say return, I would probably want to say j plus equals 1, right? Because you will always have the final subarray. And the way they said this, it's not the number of, this would be the number of partitions. I think it's saying partition into k subarrays. So this needs to be +1. And there's going to be probably something similar going on here, where I'm going to say res plus equals cur times cur plus 1. So add in the current score. Yeah, I mean, that looks good. This is assuming the greedy formulation works. Oh wait, this is not in contest mode, so I need to copy this over. Let's see, 25 looks good. 31, not good. 3, good. So what happened here? This should say the sum of everything is 7, 10. 10 times 11 over 2 is 55. So why would mine say 31? Print res. You know what it probably did? It probably is like, it's finding the insertion order. So I bet I need to have something like that in there. Because now it's saying, okay, res is 10, not res is like, without this, it's kind of nonsense, I feel like. Res is 9. It's saying that because it's taking this arbitrary range. Let's see, so we got 5, 10, 1. Now the other ones are off, fuck. This, no, I was looking at what's printing. Thank God. 25, 55, 3. I mean, I'm just going to send it and get it wrong. 47, 23. Okay, that seems workable. This seems kind of like a corner case in a way. So I should see res is like, what does calc do? Calc just calculates like, okay, you found the threshold. Now do the actual like sum calculation with that. So do the whole like subarray thing. Does this completely throw everything in the toilet? I think it kind of does, right? I think this doesn't really mean anything anymore. Is that true? I think I need to account for the fact that like, if a subarray is too large, you still have to take it, right? So here, if it's 23, like I'm actually kind of curious, like it's saying 23 is the first thing that works. But that's kind of weird. Because I think what's going on is it's saying you started with the subarray sum of 0. I think I need to modify this slightly. So you always start out with the first thing. Like I think the way that this is set up now, it will require it to include the next element. And the moment anything goes over threshold, it like packages that up and sets up the next thing. If cur plus x is greater than threshold, add 1. Okay, and then there's going to be something similar up here. Because the way it was going to do something really weird where it would just always say like, well, 47 is too big, so have a subarray of size 0. And then 47 plus 20 is too big, so have the 47 alone and then have the 23 together. But that doesn't really make any sense. 1344, 3, 55, 25. All right. Hopefully it just kind of works out and I don't have to think about it too much more. No. Shit. So what happened here? K is 3. What did it come up with? What was the threshold? It should say the threshold is, I guess, 41. I think it's tough because the threshold is, I guess, different for different parts. No, wait, what should it say here? According to what I'm saying, you're better off saying 41, 41, 6. Plus 21. 1743. So according to my formulation, that's what you should get, but this is what you do get. Can't there be many ways to achieve the threshold, like many partitions? I don't think so. I think if you're going like left to right, If you're kind of going with this idea that like everything needs to be, the sum of every subarray needs to be less than or equal to this threshold. But I think it gets tricky when it gets into like, well, I don't know. It's weird. So this is saying 41. Stop at the moment anything gets larger than 41. But I'm guessing if you said 10, 31, 47. So 47 times 48 over 2 is 24. Plus 31 times 32 over 16 is, or over 2 is 16. Plus, I guess 10 times 11 is 55. 1679. So that throws a huge wrench in my greedy formulation. This exact problem, this exact test case. You cut the farthest away for binary search purposes, but if you really want a partition of size k that minimizes the maximum sum, I think there may be several of them. This example right here, you have maybe some partition you cut sooner and it still works. Yeah, I see what you're saying. Like if at the end of the array there's like a dangling extra part, there could be several partitions within the last two subarrays. Like if a one transition from a partition to the previous one. This also just throws a wrench. I'm actually kind of surprised by that. This completely throws this in the toilet. Because this is saying, no, you do want to actually have a larger subarray sum. Yeah, I see what you're saying. Like, but this is even questioning just the optimality. This greedy formulation is just wrong. Because this is saying you'd rather construct a larger element. So I guess I got to go back to square one. I guess trying to do something greedy is not a good idea. Dutch CTF box player. Welcome. Trying to enter the minimum possible score among all valid partitions. It's getting into the battle music now. Is this only Python you're coding in? I usually use C++, but for Leetcode I use Python because it's just faster. And also for C++, I like having all my macros and stuff. And for Leetcode, they're usually more lenient with the time complexity. But not so much these days. So you can really cheese this with O of n cubed. I've heard about that as a very complex language. They say more difficult than Python. That's what they say. People sometimes say like don't start with Python, but I think that it's fine to start with Python. I think personally, I think starting with like C# or something is probably a mistake, unless you're like it's for your job. I'm stumped. That really sucks. This is like not, according to the numbers, this is not that hard of a problem. Am I again wildly overthinking it? So if you get, because I kind of did like start outlining these building blocks. So I can just get value L and R. Try to improve your skills in it. That's cool. Value of L and R in O of 1. That's fine. I can just find that. Can I use that somehow? That would mean for dp at I at j, you're at index I with j. Well, no, wait. Now I'm thinking way up here, I was like, can you go element-wise? And then I was like, no, fuck that. I think you probably could, right? You probably could say there's two transitions. There's then go to value from L to R plus 1, or there's go start value from R and on. What are L and R? Here I'm just like starting from basics and I'm just saying like for a given subarray. If you're trying to draw a partition, is there a way to just have a DP formulation? I spent so fucking long thinking this problem was different. That really fucked up. And like I spent a long time, I think, like letting that affect how I thought about it after that. After I was like, oh, the problem is something else. But I was still stuck in this weird mindset where this wasn't available to me as an idea. So if you're at some index I and you're saying I'm at 1, I've had this many, I've already drawn this many partitions and I'm at this index. Is there a way to decompose this down to say when I'm here, I just immediately add this to the thing before, or I add this to the thing after? I start a new thing here. You could easily do that with an O of n cubed state space, but that like entirely defeats the purpose. Nums at I is only 10 to the 4th. Is that useful at all? I don't think so. The sum of values of all its subarrays. If you did it iteratively, maybe there's some kind of speed up. You say, I'm at DP at L at R. If you're at DP at L at R, DP at L at R plus 1 is one option, or the minimum DP from R onward. No. That's a really confusing way to put it. Yeah, no, that doesn't actually make any sense because you don't have DP at L at R. You have DP at I at J. Man, I thought I was so slick with this and this was just completely wrong. I really want to look afterward at like why that was just wrong, because this makes sense to me. that you would minimize the maximum, but that's not right at all. Oh well. I had a solution that also made sense to me and was wrong. dp at I at j. What you're doing is all seeming very complex to me. I try to like jump into the deep end with this stuff because I find it more interesting, but or I don't know, I've been doing this for a long time, but I mean, clearly I might be a little maulding today. Value of a subarray is defined as subarray. So is there any way to possibly formulate a state space as not dp at I at j, where I is the index and j is the number of remaining partitions? I don't think so. I don't think there's any way you can encode that without that. So if you did that, you would have to have an O of 1 transition. And then that would come down to the algebra, which I did start to do, but I started to do the algebra when I thought the problem was much more confusing. I thought it was the sum of squares of all subarrays within each subarray in the partition, but I was adding an extra step. So maybe it's worth revisiting the algebra. So if you have some score for a partition, that's going to be for all the subarrays in the partition, you have the left and right bounds. And then that's the sum. Fuck. This is so confusingly written. Okay. It's gonna be a handful, but that's okay because if I write it all out, I can maybe start reducing it. So it's the sum from, I guess, for L and R, such that those are the bounds for each subarray, and then it's the I'll look at that in a second. The sum from I equals L up to R of A at I times the same thing again, plus 1, over 2. So for all L and R in the subarray. So I've already kind of, yeah. Okay. So I've already kind of decided you can just move this out because it's just inside of two sums, right? Okay, that looks good. And then I think there's something going on here where you're kind of like, I thought it had to do with the fact that this is convex. Clearly I was wrong. I hope I was wrong. Maybe I wasn't wrong. That really, really seemed like it was fruitful, but it just turned out to be completely wrong, and I don't know why. This is just blatantly like a square of a positive number. There's no possible way that's not a convex thing. So, but maybe I'll go back to that. I don't know. But maybe there's a way that I can reduce this out. Yeah. I was so sure, like, I don't know. It really seemed like one of those, but maybe not. I kind of see, like, because you're not exchanging any element between any subarray. If you were bucketing it, then it would make sense. If they were subsets, then I think this would matter a lot more. Then you would minimize the maximum, and there'd be some way to do that. But I think because you're Okay, I feel less bad then. I feel a little less bad because I just wasted so much fucking time on this. I got the other three in like 15 minutes, and this one's taking me an hour. Um, and I probably won't get it. But maybe there's a way to pull these elements out and say just like how many times are you counting A at I, right? I don't really see that though. Like I don't see how you would do that. Even if there was no +1 here, let's just get rid of that and assume that's not there. Like the other elements in your partition absolutely affect the amount that a given element will have an effect on anything. If this is supposed to be O of n cubed, I'm gonna be pissed. That's really stupid. Like, because that's obvious. That's really, in my opinion, obvious. You have dp at I at j. Your transition is O of n. There's like, that's very straightforward. I can't imagine though. They love to have it be like 800 and it's O of n cubed. That is like pretty tantalizing. This would just feel like a straight up lie if it's supposed to be O of n cubed. That alone would TLE. I had to add a trick for it to pass. Okay. If you did that, I guess that maybe gets back to the slope trick thing. Yeah, okay. Okay. No, maybe. Yeah. Maybe you could get it down to O of n squared. Because you could say, okay, well, just like ignore that for a second. You have value of L and R. And you know as L goes down and R goes up, that's going to have the effect. That's going to at least convexly, that's going to be convex with regard to this. So with that in mind, I feel like there is a slope trick you could do where you could say, I don't know. I would be so surprised if 900 people figured this out. But maybe you could say for dp at I at j, you do just test dp at I. Okay, there's two things you could do. The first is you just say, now it's dp at I plus 1 at j. You just say continue this, right? Or you say, maybe some LLMs, yeah. So you either continue it, or you say, let's see. No, that's not even, the way I'm formulating this, you're not even doing that. You're just saying, if I'm starting at index I, go to dp at k at, we'll say j plus 1. So add a new partition in. For all k greater than I. But you know that as... Do you? I don't know. I don't even think you know that. So you're just looking for all of those. I think you could do it if you had it be 2D and you had a bunch of segment trees, right? Couldn't you do that? Why would that not work? Because you're only ever changing j by 1. And in fact, no, you don't even need a segment tree. I think you literally just have a rolling minimum. Right. So if you have some like dp at k at j and some dp at k1 at j, if k1 is greater than k0 and dp at k0 is greater than dp at k1, then you just take the minimum. Okay. All right. Fair enough. All right. Okay. I feel a little dumb I didn't get that. I feel pretty stupid that I didn't get that, but that's fair. So you're just taking a rolling minimum and you don't need to think about it any further than that, right? You're just saying like start at any next index. Because you will always, for any dp at I, this is the index you're at, suffix, you'll always be able to jump to any, the only thing is k is greater than I, right? Like there's not like within a range. And even if it was that, you could just use a segment tree because you're only ever even modifying one value at a time. What about the score? Wait, yeah. Wait, yeah, this is not right at all. Wait, okay, rolling minimum. Okay, no, my original thing does still hold though. So the rolling minimum's out the window. You're right. That doesn't make any sense because you're not just taking like dp at I at j is equal to dp at k at j plus 1. You're saying it's dp at k at j plus 1 plus value, which we'll just say is an O of 1 function with pre-caching, which it is, from I to k. I still think there's something you can do with this, though. I still think you could have a monotonic stack per j in your state space, and you could say, this is convex. It just is, right? With regard to k. As k increases, the value at I at k will increase quadratically, but it will increase. And as dp at k at j plus 1 goes up, I don't think there's the same thing, but I think like this can be completely arbitrary and you still have like a slope trick. But I guess this gets back to your original question, Solaris. Like, can you do the convex hole trick with quadratic equations? I don't think you can. Because you could just have like, if you have like y equals mx plus b, and you have like, okay, for one thing, you have m0 is equal to 0, and b0 is equal to 1. It wouldn't even be this. It would be mx squared plus bx plus c. So for this, if you said, okay, that's 0, that's 1, c0 equals 0. I have to pee so bad. I'm going to get up in a second. But then for this one, if you said 1, 0, 0, then you would get something that's like, they both start at the same point. This, or let's even say this is like 0.5. So one of them is just a straight line like that. This would be line 0. Or we could even say like dp at 0. This is how it scales as you move forward. But the other one would be like that. right? So there's no monotonicity anymore. Like there still is, but you wouldn't be able to just use a monotonic stack. And I'm already like still practicing with the convex hull trick. The idea of using some weird second order convex hull trick seems at the very least outlandish if 900 people got that. Okay, I'm going to go pee and then I'm going to look at the solution. Let me get the old... There we go. You want to come in here? Okay. Do I want to look at the solution or do I just want to think about this more? I don't really want to ruminate on this. I think I'll leave this. And then, like, Solaris, if you want to give more hints or something, like, are you even aware of an O of n squared solution, or was it like just everybody that passed did some slightly optimized O of n cubed thing? Man, that's an L if I've ever seen one. Oh well. But yeah, I think I'm going to leave this. I thought this would work. Okay, we got a prefix sum. Okay. You get a score. You're binary searching. Oh, interesting. Okay, so you're saying take an index. Take a number of remaining partitions, or number of used partitions. If you're using up one partition, then just find the score from this to the end. Or else binary search where you're saying find the optimal, yeah, this did, find the optimal next index to jump to. Damn. I think you're utilizing the same thing I was kind of trying to utilize. Binary searching for the dip, ternary search is also possible. Yeah. That's so weird that, like, what happened? Where is it? I don't know where it is. Oh well. No, yeah, what happened here? Where if you're saying this is essentially a sum of squares, try to minimize any of the squares. Why did that not hold? Why would you ever want to say, no, you know what, I do want this square to be larger? Like, I would rather take away from this and add to this. Why would you ever do that? I don't know. The insight to cheese it is that if two neighboring partitions can have a smaller delta, if you transition one element to the other one, it's beneficial. Like 10 then 5, it can become 7 then 8, that's better. Yeah, I guess, I mean, that's like, I guess I took that info and I kind of went in this like, oh, okay, so there's a monotonicity and you can binary search it and you're looking for the minimum, maximum Y, but that turned out to not be right. It kind of makes sense to me why that's not right, I guess, though. Like, because if you have like, this is your distribution of Ys for some given threshold, then that's a bad distribution. Like what I want to show is like if there's some distribution like this, it's like you wouldn't want to just say, okay, well, like collect all of these together. I still don't really see why you wouldn't. I don't see why you wouldn't. If these are essentially squares, like have these be the way that you separate out your kind of histogram. Something like that. It didn't seem like that's what was going on. It seemed like what you wanted to do was like some weird thing like this, but I'm like, is this really minimizing your area? It didn't feel like it. I don't know. Oh, that's whack. That's crazy. I gotta get my phone charger. No, I don't have to get my phone charger. Because I got a new one. Yeah, I'll take a look at your AC. Okay, accumulate. So you got your score. You say for every beginning index, for every possible amount of partitions you have remaining or you have spent, do that. The limit is prefix sum at -1 minus prefix sum at I plus v minus 1 over v. What is this line doing? If a partition increases past the limit plus m, it's always beneficial to transition something from it to one of its neighbors, I think. Oh, so you're just saying like if it's too large. So you're finding the largest element where you're like, I would rather not make this bigger than that. How does that really even optimize though? O of n log the sum. WQS. What is that? Known as aliens trick or slope trick in competitive programming. Okay. I haven't heard of it referred to as that, but that sounds like... We observe that the score function is convex. This means the marginal reduction in score decreases as we add more partitions. Okay. This property allows us to use the alien trick combined with the convex hull trick. Combined with it. So you're doing both. Because it seemed like, Solaris, you were doing more the convex hull trick of like per state in the state space. It's written with AI. If they got it, though. I mean, if they got it, they got it. Hull deck. They're definitely doing like the convex hull trick. This looks extremely written by AI. Yeah, that's fair. I mean, I guess maybe this is getting into the noise of the LLMs, but if they're saying they used both the alien trick, which in my mind you're binary searching for a parameter in your DP state space, and then you're recalculating to see if that state space is more optimal than another one. That's what I was doing. And it seems like what you were doing was more the convex hull trick, where you're saying, I will optimize my state space itself by keeping track of the linear relationship between each state, DP at I at j and some other DP at k at j plus 1. This seems very AI-ish. Min cost with k partitions. Okay. Core insight, convexity, extremely AI. Convexity transformation. Using the alien trick, we remove the k loop. Now we just need to solve the unconstrained problem for the fixed lambda. Roughly quadratic. However, the transition equation can be rearranged in the form of a line equation. Yeah, that's affine. Okay, at least I was on the right track. I mean, because the slopes and query points are monotonic, we can use the convex hull trick using a deck. Okay. Okay, yep. Imagine an alien says is LLM. Does it say that somewhere? So, okay. So they fully do, at least this solution, if it works, I don't know, fully does both use the alien trick and the convex hull trick. That's some next level stuff. I don't feel too bad about not getting that. That's my cope. Whew, good lord. I'm going to have to revisit that one. So they were binary searching for the threshold. Is that right? Let me look back at that. What even was the alien trick part of it? Because the convex hull trick part, that makes sense to me. They're saying the recurrence relation is quadratic, therefore it's convex. What's the idea behind the alien trick? You can make as many partitions as you want, but for every new subarray you create, you must pay lambda cost. Oh, that is different than mine. But how, since we have parabolas and not lines? Shit, you're right. You got LLM bamboozled? I don't know. The moment it tells me you're not imagining this, yeah, then I got. But I don't know. Is it? I don't think the fact that it's quadratic invalidates it. Right? I'll at least look at some other solutions. I mean, does this person's solution at least work? If it works, then that does actually kind of... if it doesn't work, then yeah. Okay, it does work and it is fast. So clearly it's doing something right. right? And binary search to find the correct penalty. That's not the part I care about right now. The convex hull trick thing is the part I care about. Find the best line for the current x. Since x is increasing, the optimal line moves to the right. I just don't think it matters that it's quadratic. Right? What is the line? Dot eval x, dot eval x. What the fuck is p at I? Whatever. Calculate dp value using the best previous state formula. 2 times dp at I is equal to p at I squared plus p at I plus 2 times the lambda plus the minimum of the slope times p at I plus the intercept. And then you're adding the new line in. What is the variable of the function there? What is the slope and intercept? True score, not relevant. Using the alien trick, remove the K loop. Okay, so dp at I is equal to the minimum for all j less than I of dp at j plus the value from j at I plus some lambda. That's not relevant right now. Val at I is roughly val at j at I is roughly quadratic. No. They're saying the complexity is roughly quadratic. They're saying this is the score, which also scales quadratically, roughly. However, the transition equation can be rearranged into the form of a line equation, which they're saying is 2 times dp at I. So I'm guessing they just straight up took out the over 2, right? Then this is not linear in j because val at j at I is quadratic for a given I in variable j. I'm willing to engage a little bit further with like what they're saying is equal to constant at I, doesn't matter, plus the minimum at j for all of this where they have p at j squared. So this is just not a line. But they are saying the slope is monotonic, which it is, right? The slope itself is monotonic. Let me think about this actually. I think you can still do it if the right. Oh, do they use the convex hull trick on the derivative? So the slope is that monotonic since prefix sums p at j increase. Because the slopes and query points are monotonic, we can use the convex hull trick to find the minimum in O of 1 amortized time. I guess I gotta dig through the code more. So there's a lot of stuff they're referencing here that makes it difficult to like really see what they're talking about, but find the best line for the current x. Okay, what are they defining p at I as? Man. Alien trick Lagrange multiplier. Is that the right way to think about that? My vague understanding of Lagrange multipliers tells me, yeah. I think I literally have the 3 blue 1 brown tab open somewhere on the Lagrange multiplier. Sum of individual squares. This creates a convex curve. We want to find the optimal point on this curve where the number of partitions is k. The drawing doesn't make sense. Yeah, I'm not even trying to comprehend. Do they even reference the P though? I feel like they don't. I feel like probably this person said solve it, and then they decided I can get clout because I like did well or something. So then they said like explain it. Kind of interesting. They made YouTube videos too. I have to say my pet peeve is like Manim style, like when people use this animation API and they use it with LLMs. I can't stand that. So a line has a slope, an intercept, and a partition count. You can evaluate, given an X, but why did they use AIN? Okay, the key point seems to be the transformation of the problem of partitioning with exactly K to partitioning in any number of partitions, but with the penalty cost lambda. That's what I was trying to emulate. I was trying to say, like, if we go back, remember when I had like calculate and check was kind of doing the alien trick thing, and calculate was kind of doing the, I guess I should have included a convex hole trick on there. Although the way that they're doing lambda, like by introducing an artificial penalty, that is different than what I was doing. What I was doing was saying, introduce an artificial constraint on the maximum subarray sum, which is different than a penalty on the square. The minimum penalized score, the optimal number of partitions used. The note is 100% LLM. This seems extremely LLM. I doubt this person knows at all what they're talking about. But they queried it, so the LLM probably does. Check intersection of 3 lines for convex hole maintenance. Returns true if the line in the middle is redundant. Okay, so Solaris, you and I were talking about how does the convex hole trick work if you're using quadratic functions. I think this is it. I think you're saying you're comparing 3 things. We multiply everything by 2 to only work with integers, it said. Well, you never know. X times x plus 1 could always return a fraction. That's a joke, I can't. Intersection formula comparison to avoid division. Not really relevant. So, is a line redundant? Okay. Solve the unconstrained problem for a specific penalty lambda. Okay, that's fine. Solve with penalty. So this is the prefix sum. It's just straight up the prefix sum of nums. The redundancy check is probably optional. Okay, well, at least I got to the bottom. Okay, so P is a prefix sum on nums, just straight up. So we're saying get the prefix sum of literally everything up to this point. This part makes a lot less sense to me. So 2 times dp at I is the prefix sum at I squared plus the prefix sum at I plus 2. If my algebra is right, this would be, is there any way to factor this into 2 polynomials? I don't think there is. Right, this is prefix, if we say prefix sum at I is like y, that would be y squared plus y plus 2. No, I don't think there's a way to factor that. Oh, no. 2 times lambda. What am I talking about? Prefix sum at I time squared plus prefix sum at I plus 2 times lambda plus the minimum of slope times prefix sum at I plus intercept. I see you. I know. Good boy. Add a new line for the current state I. I'm not really understanding this one. From is equivalent to one of the well-known variations of the partition problems in which we determine the minimum sum of the squares of each of the sums of each partition. The interested and capable reader will be able to prove this assertion with elementary algebra. So I felt like I got to that. I felt like that made sense to me. The idea that you have an optimal solution that's going to roughly correspond to a sum of squares, and a sum of squares you can show is optimal when each element, the maximum, is minimized. That feels very similar to the logic that I was following. Also, this sum of squares function is convex, so the convex whole trick applies. I guess I'm not an interested and capable reader. But we saw that didn't work, right? Well, something you pointed out was that, like, I don't think it's good enough to, like, test that with a... I think you have to do the lambda, like, alien trick that the previous one was talking about. I don't think you can have a hard cutoff threshold because you get something like this. Where is it? You get this. Where over here... there's a different threshold that matters where you're like, we want to split these, but then over here, you might also want to, like, I don't think the same threshold applies. So I don't think it works to say the minimize the maximum subarray sum. I think you want to say optimize the sum of squares given a penalty lambda that you then also binary search for. Convex whole trick and convex CHT and convex whole trick doesn't mean the same thing as a convex function. The convex of convex whole doesn't mean the same as the convex of convex function. That's important to point out. That's a good point. But I don't think that matters here. Like, yeah, I agree with you. Like, the convex whole trick requires linear functions, right? Not convex functions for this exact reason. But I think that's why there's that extra step. Like, you can't just do convex whole trick. And the side I was coming from is like, you can't just do the alien trick. Or I think you kind of can, but you can't do it the way I was trying to do it. A convex is just a set of barycenters of some points. Yeah, no, I agree with you. I'm not trying to say like convex equals convex whole trick, but oh, you're probably pointing out in this person though, when they say the sum of squares function is convex, the convex whole trick applies. Yeah, that's a weird thing to say. I could be wrong, but I think the time complexity is O of n squared times k, and the space complexity is O of n times k. This person seems to... This at least seems not LLM generated, right? So they're saying, go by k. For each I, why would they think this is O of n squared times k? Why would this not just be O of n times k? Cur m, cur c, while length of q is greater than 1, do all that. But they're writing the function. Oh yeah, I pointed that out too. That's completely wrong, right? That's not the reason why it applies. Yeah, and they didn't use convex whole trick in their solutions. So why they talk about it in the editorial, or did they? Yeah, I get the sense what's going on here is this is someone that like I could see this being someone that the LLM found a solution and then they are like trying to make sense. They're like trying to explain it. Maybe. Maybe this is a real person. I don't know. Um, it's really a red flag for me though that they said I'm pretty sure the time complexity is O of n squared times k, when in my mind it seems pretty obviously not that, right? Like they have okay, this is O of k, this is O of n, and then everything in here is just like popping a q. It obviously amortizes to O of 1. So like I don't know where they would get that. But he is rank 81. Yeah, he's really been submitting a lot, I guess. Well, okay. No, this is probably actually I take it back. I don't think this person's using LLMs. Because this is 2022. This is before they were able to do that. And they also did like this in my mind the explanation here is not written by an LLM. I don't think an LLM would say this. I don't know how to write editorials. Yeah, I guess. Okay, so what's their code actually doing? They also take a prefix sum of nums. Okay. List map taking something to the taking something squared is what this is doing. So square all of the prefix sums, right? Which makes sense. You're saying like, no, that's really weird. What the hell? Why are they squaring it? Why define that pow2 function? Maybe it's some weird optimization if you use Python a lot. I don't know. But that's so weird they would square it too, because that's not even what the question is asking. The question is like x times x plus 1 over 2. So why would they just square? Like that's just x squared. Okay. Does this work? If this doesn't work, I'm just wasting my time. Okay, so they square the prefix sum. That's fine. That's not. I don't know why they would do that, but whatever. Previous DP, you get that. You're filling up the new one. You're saying take an extra step everywhere. And you have a queue. This is too quiet now. Is this showing up? No, not really. This isn't, I think this is not showing up at all. Right, or maybe it's just really quiet, I don't know. Oh, there it is. Oops. Sum of squares is a different formula, I think. That's fair. Yeah, maybe that's not really what I'm assuming. I assumed what it's saying is current DP is saying like, okay, if you took if k was equal to 1, right? I don't know how 900 people solve this. 900 ChatGPT users, I guess. Like, no fucking way. There's been like one problem on Leetcode that uses either of these. I've never seen a convex hull trick problem on Leetcode. And I've seen like one alien trick problem. Oh, here we go. Okay, most common. That is weird. I don't like that. Okay, I kind of believe that this is like a real person though. So current DP is just every prefix sum squared. And then you're saying for every new partition I'm going to add in. It seems like this is saying DP at I represents the subarray value up to I, right? So then they're clearly doing some sort of convex hole trick. They don't seem to be doing any alien trick at all. So like a plus b plus c plus d squared minus a plus b squared. There's a name for this trick. Let me go here. I was like looking into this. There's like a name for this kind of thing. New thought. I think this is what's coming to mind. But Firefox Nightly is really weird. I was looking into this recently, and this really reminds me of this. Knuth's optimization, also known as Knuth-Yau speedup, is a special case of dynamic programming on ranges that can optimize the time complexity of solutions by a linear factor from O of n cubed for standard range DP to O of n squared. So if you have something that is my understanding is, if you have a convex function, I don't really think that's what's going on here, but it seems very similar. If your cost function is convex, and you're smart about it, you can reduce the transition by O of n. We have exactly that. That's the Leetcode problem, what I was just looking at. Does C have to be convex? Cost of B and C is less than or equal to cost of A and D. And cost of A and C plus cost of B and D is less than or equal to the cost of A and D plus the cost of B and C. The quadrangle inequality, as it's known. One is for sure true. Two is, I'm fairly certain, true. And this is actually what I was kind of basing my thing on, where this is saying you would rather, it's a lower cost, A to C and B to D. So you're saying take the overlap where it's two sort of big ranges rather than a really big range and a small range. It's saying you would rather have the sort of big ranges, aka the cost of this range scales quadratically with the bounds, the distance of the bounds. Or not even scales quadratically with the distance of the bounds. If you set one bound, it scales quadratically with the other bound. That's what this is saying. The most common application of this optimization is range DP with the given transition. The only difficulty is in proving that the cost function satisfies the given conditions. The simplest case is where the cost function is simply the sum of the elements of the subarray for some array, depending on the question. However, they can be more complicated at times. Note that more than the conditions on the DP transition and the cost function, the key to this optimization is the inequality on the optimum splitting point. In some problems, such as the optimal binary search tree problem, which is incidentally the original problem for which the optimization was developed, the transitions and cost functions will be less obvious. However, one can still prove that the optimum for I to j minus 1 is less than or equal to the optimum for I from I to j is less than or equal to the optimum from I plus 1 to j, and thus uses this optimization. They even took the textbook case. That's why the LLM got it easily. The problem is like the textbook case of this trick. Yeah. It's sort of. There's this weird though. It's just simply the sum of the elements of the subarray. That's their cost value. Which, if I'm not mistaken, actually means that this is not less, this is always equal to. It's less than or equal to, but it's equal to. So that's like actually stricter. I don't really love that as a case because like ours is the sum squared basically. So it's not just the sum, because when it's the sum, then you can use like the convex hull trick or something. It's not just the sum, it's the sum of integers up to the sum. Yeah. However, they can be more complicated at times. Let's process the dp states in such a way that we calculate dp at I at j minus 1 and dp at I plus 1 at j before dp at I at j. And in doing so, we also calculate the opt from I to j minus 1 and opt from I plus 1 to j. Then for calculating opt from I to j, instead of testing values of k from, so it's saying instead of trying to partition k, some kth partition between I and j, you only need to look at information that like prefix information that was stored in opt from I to j minus 1 and opt from I plus 1 to j. You don't need to individually try every partition. That would be O of n cubed. Right? You have like 2 bounds in a partition. That's like 3 indices you have to test. This is saying there's a way to not have to test every partition in between 2 bounds for some dp at I at j. We only need to test from opt I to j minus 1 to opt I plus 1 to j to process I and j pairs in this order. If to process I and j pairs in this order is sufficient to use nested for loops in which I goes from the maximum value to the minimum one and j goes from I plus 1 to the maximum value. So I think opt represents the index of the optimal thing. It's the okay, not all k's are tested. Yeah, I think so. Opt, I think, is keeping track of the furthest out index you could care about and the furthest in like suffix index you could care about. Good Lord. Index, not number of partitions left. Oh. No, yeah, maybe I do have that wrong. No, I'm pretty sure this is like a divide and conquer formulation. This is saying I is the left bound, j is the right bound. dp at I at j, yeah, right here. So dp at I at j, if you imagine I and j, let's say, are indices in an array, is the minimum for any k between I and j of dp at I at k plus dp at k plus 1 at j. So you split your range from I to j in half. You said, okay, make a new partition at k plus the cost from I to j. Oh, kind of what I was trying to do with my binary search. Yeah. Your binary search, I think, was closer to this than mine was. This is one of the more confusing ones. If I was to make a tier list of like the most confusing algorithms, I tend to find graph algorithms and like range query structure algorithms like Fisher-Hoon and segment tree type stuff. I tend to find that easier relatively. I tend to find this stuff harder. I think this would be just below like weird string algorithms for me. I will just never understand suffix automata. Solving a good problem next. Yeah, I can try to solve this. Jerry and Tom. Jerry and Tom are playing a game on a directed graph G with n vertices numbered 1 to n. For every vertex 1 is less than or equal to u is less than or equal to n, there's a directed edge from u to u plus 1. Okay. In addition, there are m extra directed edges. The ith extra edge goes from ui to vi, where 1 is less than or equal to ui is less than vi is less than or equal to n. So immediately there are no cycles, is what I gather from that. Because everything goes from u to u plus 1. And then there are extra edges that go from u to some u plus something. V minus u plus v minus u. So the whole graph only goes in one direction. The graph G has the following special property. There do not exist two directed edges, ui to vj and ui to vi and uj to vj, such that ui is less than vj is less than ui is less than... Okay, the u's and v's are kind of confusing me. The graph has the following special property. There do not exist two directed edges. So we're looking for two edges that don't exist. Am I not given the graph explicitly? No, I am. There do not exist two directed edges, ui to vi and uj to vj, such that, so if this is true, then I know that two edges won't be given to me. ui is less than uj is less than vi is less than vj. Okay, so it's saying not only do I not have cycles, but also, if I'm reading this right, there's no hops. You'll never be given an extra edge. I might as well just draw this out. So we're given a graph, directed graph. We start out, we get the linked list. Every u goes to u plus 1. And then also there's ui goes to vi, where we could have like this. But we can't have this. Or I'm even going to do that. We can't have this. Or maybe I'll have this to be like really the most base case. No skips. Okay. At the beginning of the game, Jerry and Tom stand on vertices x and y respectively, where x doesn't equal y. The game proceeds in turns, and each turn the players behave according to the following rules, with Jerry going first, followed by Tom. Compute the sum of some big thing, some function. Okay, f of x and y is something. So Jerry must choose one outgoing edge from his current vertex and move along it to its end. If his current vertex has no outgoing edges, he stays where he is. Tom may choose one outgoing edge from his current vertex and move along it to its end, or choose not to move and stay where he is. Okay. I think I see where this is going. Like the moment there's a bottleneck, then I'm guessing Tom wins or something. If at the end of any turn, Jerry and Tom are at the same vertex, then the game ends immediately and Tom wins. Okay, yeah. Otherwise, if Jerry is initially at vertex n or reaches vertex n at the end of any turn, Jerry wins. Okay. Note that after a turn, both Jerry and Tom are at... If after a turn, they're both at vertex n, then Tom wins. Okay. Throughout the entire game, both players know each other's locations. It can be proven that the game will end in a finite number of turns for a pair of integers for all x and y within 1 to n. They'll play a game where Jerry's on x, Tom's on y. Tom wants to win, but also wants to minimize the number of times he actually moves, that is the number of turns in which he changes his vertex. Staying still does not count as a move. Assuming both players play optimally, let f of x and y equal 0 if Tom cannot win. Otherwise, f of x and y be the minimum number of moves Tom has to make in order to force a win. If Tom wins under optimal play, Jerry will still try to maximize the number of moves Tom has to make. Okay. Compute the sum across all x and y of f of x and y. Okay, that's kind of understandable to me. I feel like I've already made a few kind of important assumptions. So the moment Tom gets to one of these vertices, he just instantly wins. Does he go first or does Jerry go first? Jerry goes first. So if Tom can make it to one of these and be after Jerry, if Jerry is like over here, then Tom will win. Because there's no way to skip over any a vertex like this. You have to pass through it. And Jerry will have to go through that. Tom can just wait there, including the final vertex. You can have like 2 and 7 and 1 and 8. Yeah, I was just thinking about that. That's a good point. You could have where it's less than, less than, less than, less than. So you could also have like this. And then if Tom is here, he only wins if Jerry was here. Right? I don't think there's any world where Jerry would choose to be there. Jerry would always have done this if possible. The only way Jerry wouldn't take this bridge is if Tom is already there. Is that true? Or is there a world where Jerry wants to like stall for turns? I don't think there's any world where Jerry wants to stall for turns. Spooky. So there are going to be ranges where Jerry wins or Tom wins. What are the constraints? N is 10 to the 5th. M goes up to N minus 2. So let me think about this exactly. There do not exist two directed edges. So if you have A is less than B is less than C is less than D, and you have two edges between them, this is the only one that's not possible. Everything else is possible. And let's see. There's only a few other possibilities, if I'm not mistaken. There's A leads to B, and C leads to D, and there's B leads to C, and A leads to D. I think those are the only three things that could happen, because also the edges can't go backwards. So you kind of want some sort of query that's like, let's say Tom was here. You want some sort of query that's like if Jerry was in between these points, what's the furthest Jerry is going to be able to jump to? And the moment that that furthest point is like before this. Yeah. Then Tom wins. So you'd say, I guess for how would you do that? What's the furthest point x can reach that doesn't go through y? Which you could get. You could say, so if you have some x is less than y, I think if you have, so just right off the bat, if you have x is greater than y, then Jerry wins. Like, just automatically. Because they can always just do the exact same turn. Tom has to be ahead of Jerry. So this handles this. We don't really care about that anymore. Then it becomes, if x is less than y, is there some way for x to be greater than y but not equal to y? So x, when does x lose? If, I think you could say like max of a from x to y is less than or equal to y. So you're like, if there's all these jumps here, something like this, and like x is here and y is here, you'd say, okay, well, like, is there any way for me to even skip y? No. So then x loses on the spot. Is there ever any world where anything else happens? Yes. Because x could be less than y, but be like here. And then in that world, maybe y has to like take a bunch of jumps. But x can just jump ahead of y. You need to calculate that in O of 1. So maybe you like go for each x. There's kind of a few options. There's like for each x. And I think if you could calculate this in O of 1, if you could calculate this efficiently and just say there's exactly this many y spots that don't work, like every y after here doesn't work because that's the furthest I can get. But I don't even think that's the case. Because you could have like a big stretch here. So any y here doesn't work because you can just hop over it. And then what if you had like another hop? And then there'd be some point where you'd say any y here doesn't work because it's going to be able to reach there. Any y here doesn't work. Or what am I talking about? Doesn't work means you can hop over it. So any y here gets you. Any y here gets you. Any y here doesn't work. So I guess one option is you say for each x, query all valid y's, right? The other option is you kind of do the opposite, and maybe that's more useful. Query all valid x. So I guess what that would mean, it's crazy how often we have the same thinking process. Did you went to grad school for math, right? Or computer science? Let's see. So if we have the same thing, let's say like this, and then you have something like this, and then you're here, and then you say for all y, two years of math, and then 3 years of almost any CS, of almost only CS. Even though I had to retake my last year twice because I couldn't find an internship. Oh, that's rough. Was that like during COVID? So if you're at this y, you're just going to say, look for any x where the maximum x that can be reached is less than y. But then that's not really enough. Because this is if you were saying, because there's some x here where it goes across to here, and then here, and then it goes across to here, and then it goes across to here, but in that time, you already reached the end. Like 1 year after that, but there are still restrictions. Yeah. That's rough. Yeah, I graduated pretty much exactly into COVID, and I just like, it's tough out there. Let's see, so then you would need to calculate, okay, for this y, I can step forward a certain amount. You would just always want to step forward as optimally as possible, right? Maybe I'm thinking about it the wrong way, though. Maybe the right way to think about it isn't, can you get to a spot and then sit there? I think the right way to think about it is, what's your distance to the end, right? Because if you were here and any x before this point is just like fucked over because you can just sit here and wait for them, you could just sit here and wait for them, but for any moment where you're just sitting waiting for them, you could also just be hopping forward and you would be ahead of them. So there's no world where you would ever optimally wait and not optimally go to the end first. Because if you can optimally wait, they have to go through this point, and if they have to go through this point, then they're purely behind you, so you might as well meet them at the end. So if you said, how long does it take to get to the end, you've encompassed all other points where you could catch the person. So I think you can collapse down you can say the only heuristic I care about is what's the distance to the end, right? And then you could say, okay, for a given y, or x, I don't even think it matters at that point. For a given y, I have some distance to the end. So dy is equal to like 10. And then you're just looking, I don't even think it matters if it's here or wherever. You're just looking for all dx that is less than 10. Right? And I think that works out nicely. Because if it was less than or equal to, if dx was also equal to 10, then that would mean there's some point here where it's going to reach the end in exactly 10 steps, but they went before you. Jerry must choose. The game ends immediately and Tom wins. If at the end of any turn, note that after a turn, if both Jerry and Tom are at vertex end, then Tom wins. In each turn, players behave according to the following rules, with Jerry going first. So I think it's counting a turn as both of them go. This is one turn. So that would mean that this is less than, right? If Jerry's already here, if Jerry's 1 point away, okay, here's the end. dy is 1. And then there's a bunch of other random points that are leading into this, let's say. So then there's some other dx that's 1. It's not that simple though. The problem is saying the minimum. So it is specifically saying you would want to wait here. No, it's not saying you would want to wait here, is it? Yeah, it is saying you would want to wait here. Because if you wait here, the game is going to end in less turns. But also you could say, if I were to wait here, yeah, this is what you could do. You could say, if I were to wait here, then all of these would take the distance that they have to get here. To end. So try waiting here and see how many wins you get. How many things have to travel through this point. But you wouldn't just say try starting at this point and waiting at this point. I think you would say for any other y prime that's going to y, try traveling to here and then waiting. For any y prime that would have traveled through y to some further point. What happens if you just go here and wait? Let's see, so their distance to the end is going to tell you whether Tom wins or Jerry wins. So just straight up, if dx is less than dy, then the answer is 0. If dx is greater than dy, the answer, let's say, is either already pre-calculated by some y prime is greater than y, or is the distance from x to y. So wait at y. So if you started at the end, you could just say, how many points can reach the end before all dx? That's the loosest possible formulation. You'd say, okay, he's just trying to win. Tom's just trying to win. So just jump to the end for every single point. Don't ever wait. And then you could say, okay, but look at the end minus 1. How many points that could have won by waiting here? Right? So what's that going to be? If you choose to wait here, then there was some previous x prime and y prime I mean, yeah, you for sure want to be thinking about y's choice. You don't want to be thinking about x's choice, because x will always just try and surpass you. Is that true? No, it gets really tricky, because I feel like, yeah. Yeah, you're saying if y made this choice, how many x's for sure can't win as a result of that? Maybe there's something in dx minus dy. Because if you can reach the end, let's say dx is 3 and dy is 2. Or let's say dx is 2 and dy is 1. There's a world where you have this, and you say you could go to the end or you could just wait here. So the right answer should be 1. But there's another world where you have this, in which case the correct answer would be 2, because you have to travel 1 and then wait. But perhaps you could say, for any given spot, if you choose to try to wait here. So I think I've come up with a solution that is able to find whether you can win in O of n log n. That should be fine. But the minimum number of moves to win I don't think it's so. I think that part's still up in the air. yn log n. The basic idea is for any given. So you have A, and then for a given point you have di, distance to the end, right? And that's just going to be informed. You can just find that. That's not possible, but you can just find that. The minimum distance to the end, I should say. And then for any given dy, for any given y, find all dx such that dx, I don't know, yeah, I'll say x such that dx is greater than dy. What did I decide on? Greater than or equal to? Or the number of winning positions for a given y. Yeah. So like solving that subproblem, you could do with like a segment tree. Right? You would say, find all I think I have an idea, but I think you use a segment tree, right? You just say, what's the total? Yeah, that's number of elements to the left greater than self. Or to the right, too. I don't even think you need a segment tree for this. Because you could have something that's like this. And maybe you have something like this, too. And then you'd say, okay, well, like, these elements can make it. And these elements and these elements. Maybe we even say, like, y is there. And these elements. No, what am I talking about? Oops. Yeah, it's like this. And also like these elements. But then if you're here, then it's going to take you too long. And by the time you get there, y will have gone to here and then gone to here. And then there's no winning. So like it's just going to be all the elements where their distance is greater than y. And you could query that, I guess, with you could do that any number of ways. But I think you do start to care about whether it's to the left or the right. I think what you could say is like, what's the number of elements that index y dominates? Like that have to go through index y. You know those are only going to be on the left. And then if it needs to go through y, you already know that dx is going to be greater than dy in that context. And then you would say, okay, well then don't go forward, just stay at y for those ones. So I think what you would do is you would say n dominates everything. So you start at n and you say like res is the sum of all elements that are greater than 0. That's a weird way to put it. Because it wouldn't really be the sum of all elements greater than 0. It would be the sum of all elements greater than some other element that represents a starting y position that ended at n. But no, that's okay. You'd say res is sum of dx is, well, for all dx, let's say in A, except actually it's going to be for all dy in A, the sum of all dx in A, if dx is greater than dy. And you could initially calculate that by just iterating through every every element and saying try getting this to the end, and then waiting for dx to get there. This will be the answer if every single element just jumped to the end. Okay, I'm gonna go to the bathroom again. I'm going to solve this one and then head out. But I think then what you could say is you kind of are like, you're like eroding away. So if you have some graph and you just calculated n, and now you're at n minus 1, you're saying, okay, I already know the amount of things that can optimally solve this by just jumping to the end, but how many things can optimally solve it by jumping to the end but then stopping here? So you would need to say how many elements you would always say, even if you were like here, and there was something like this, you would have already previously eroded away these. So like the way it would work is you would say, okay, I'm taking away 1. Like you only would have moved up 1 to the next thing and then stopped if you could have. So for all valid dx, just move 1 less. So the number of valid dx is going to be all dx that is greater than dy such that y dominates x. So all elements that are further from the end where this dominates that. So is there a way to say what are the number of elements that this element dominates? I think you need more than this to, maybe you don't. No, I think this is okay. So the number of elements that this dominates, I don't even think you need greater than dy. I think this will always be true if y dominates x. So you start out, you find all dx is greater than dy, and then you say, okay, for here, how many elements does this dominate? The number of elements that this dominates, necessarily you could have just stopped here. But no, you do need something like this, because you need some way to say it's dx prime and dy prime. These were some previous x and y that you started at, where you're now stopping at this y, and you're saying how many elements does y dominate? What are you counting? So I'm saying, like, if you have your big array, right, all the vertices, you have the nth vertex. I've found a way to say, okay, well, just every single time, always try to hop to the end first. That's always optimal. Try to do that, but that's not going to be the minimum number of moves. So now the question is, how do you get, this would be the, I guess, maximum number of moves, but like if you played it as safe as possible, how do you then successively constrain for, like, wait at earlier and earlier places? Because, for example, if you had some bottleneck right here, what do you mean by hop directly? What I'm saying is, like, if you have some bottleneck here, you know that all of these, you're better off just waiting here, and all of these will come to you, and that's the minimum number of turns, is if you waited here. But I'm saying, like, the way to find just, like, all of any solutions at all is if for every single turn you always just hopped to the end and you measured what's the distance to the end. And if you measure it that way, then you know, like, the total distance to the end, or the total number of dx greater than your current dy, the sum of all dx greater than dy for all dy, this is going to be the answer if you just hopped everything to the end. Like, or, you know, you did whatever, but you made it to the end first. And then that gets you the answer if you just, for every single valid thing, jumped to the end, or like made it to the end first somehow. And then I'm saying, like, that's easy to get an O of n. Or O of n log n, I guess. But yeah. Yeah. And then the question is, like, okay, well, what if you waited here? Because, like, let's say this was the whole graph, was just like these lines or something, or these lines. Like, you know, when you're here, you don't want to jump to the end. Or even more saliently, like, when you're here, you just want to wait here. You don't want to, like, jump to the end and wait for all these to jump to the end. O of n only. The sum for all dy of the sum for all dx. I guess, sorry, what this would really be is dx if dx is greater than dy. But anyway, then the idea is you say, okay, well, yeah, like, if you're here, don't jump to what happens if you don't jump one forward? What happens if you just waited here? So that's where I'm saying all of the indices where you could have waited here instead of jumping one forward, you know, you're only going to jump at most one forward. And then that's already some pre-calculated cost where you either from there jumped forward or waited. So that's not really relevant. The only question is, do you make that one jump or do you shave that off by waiting here? Right? Yeah, because for any place where you could have just waited here, that also necessarily means there was some future thing that this directly points to where you could have just waited there. And you did, because you calculated that. And that's kind of the recurrence relation that makes this work. And then the question is, do you wait here? And if you wait here, then you're shaving off. You didn't jump one forward for all of the indices that this dominates. And it's a little bit confusing because you're saying, okay, it's all of the y indices that this dominates. I guess times the number of x indices above those number of y indices. But I think that's still okay. I don't know. It's kind of confusing, but you have a number of indices that are dominated. So let's say like all of these, right? All of these you could just wait here. And then you're saying, okay, for all of these as well, there's a bunch of other points where you could start and get here first. AKA get to the end first. Because this is going to have some dz, let's say. Or no, this is dy. So there's going to be some series of dx's that are like dominated by y. And then there's also going to be some series of dz's that are just less than dx. dz's. Oh, it ended. And then you're looking for the number of dx, dz combos. So res minus equals one such that dx is greater than dz and dx is dominated by dy. It has to go through this point. So can I calculate, if I calculated each of these individually, does that help me? It's kind of weird. It's like a 2D query. The sum of all sums. Well, it's not the sum of all sums. And maybe this is where actually what you're pointing out, where it's O of n, not O of n log n, is helpful. Because if this is O of 1, maybe you can fit this into a segment tree query. Because it's the... yeah, actually, I think that's not that bad at all. I think that's not that bad because you can as you decrement take away elements. No, because if there's some big thing here like that, then you're only querying like this range kind of. But I guess you know that it will always be a contiguous range, right? I actually don't know if this works. No, this does. But I think it no longer holds that it's the distance to the end. It's the distance to this point. Because you could have something that's like that. And then you would say like, okay, there's some X and Y combination that could have stopped here, right here. But then there's also some X and Y combination where like this is dy and this is dx, and this can reach the end first, but it can't reach this point first. I think you also want the maximum dy and minimum dy for every y. Yeah, I'll just keep thinking about it. Because also, I actually think that I'm missing a piece, which is in a way you only care about the minimum, but where am I looking? Right here. If this is x and this is y, initially they're both going to be like, can we make it to the end first? But y can immediately make it to the end, and then x is actually just going to take the maximum amount of time, which is n minus x. Or I'm sorry, x is going to take the maximum amount of time. So I think my equation here, wherever it is, right here, dx such that dx is less than dy, it's not really this. It's n minus x such that dx is greater than dy. And again, I think you could query that with a segment tree. I don't think that's the end of the world. Why n minus x? N minus x is like, if n is here and x is here, if it has like 10 steps to make, right? It's always just going to be like the most Jerry can possibly draw it out is just by stepping one by one. That's just like me going back and correcting, like, actually, if Jerry knows he's going to lose, he's always going to step it as slowly as possible. Oh. Okay, that changes it. Interesting. So Jerry doesn't have to, or Tom doesn't have to wait for Jerry to take move and move after move after move. So then my initial thing was a lot closer to the correct answer. Then this would just be dy, not dx or x. It would be d or n minus x or anything. It would be dy. Okay, thank you. I missed that. So Jerry would just say, okay, do one move. And then, or Tom would say, just do one move and then you're here and then you wait and you don't have to do anything. Okay, in that case, everything still holds. And in fact, actually, that makes this much easier to calculate because you're saying, I know I'm multiplying everything by dy. So just have this be a sum of a sum and then dy times that. Right. So that actually, that makes this, I think, simpler. Okay. And then you're saying for each point, how many things can I just wait here at? How many things can I shave off one move? I've already kind of deduced that you can shave off one move if you did just shave off one move. Like, if it was like this, then assuming you could formulate a function that said you dominate all these things, you don't have to move forward, you would have said that here as well. So you're removing exactly one move from your own move pool. I guess it's an ability draft reference. And then still complicated to calculate that though. But how large? Well, dx and dy can only be up to 1e5, right? So as you step backwards, no. I was going to say you could remove the values you've already seen. But I don't think that works. Because again, you could have something like this, where, let's say that's not x and y. Let's say x and y were like, this was y. If x was here, x could just clean jump over y, and then there's no hope. Well, wait, but you already would have calculated. You actually already would have figured that out, though. You already would have found those. No, I still don't think. I think that's not the best example, but I think if you said like y was here and x was here, then you would say, well, it's true that y does get to the end before this, but it doesn't dominate. If you just tried to wait here, then this would just like take its time, but it would skip over you. So query only the x's. I don't even want to call this y. I want to call this z. This is like the potential waiting point. Query only the x's that are dominated by z. And then, based on those, query the number of y's that are also dominated by z that are closer to z than x. Right? So if you said, okay, this x, and let's say this y, does it matter if the x's are dominated by z? Yeah, it does. Because, or did I say x's? I meant y's. If you said like this y, the distance to the end is smaller, but this y would still just want to hop there, and that's the best move. And you don't want to mess with like trying to get here first or anything. So you're looking for the count of y's that are dominated by z that are... No, that's a bad way to formulate it. You're looking for the number of xy pairs that z dominates such that dx is greater than dy. And then you could break this down into for each x, for each y. Is it better to say for each y, for each x? Maybe you could DFS and you could say this domination quality, if z dominates x and y in the DAG, then that means that, and I think especially given the structure of this graph, that means that you could like divide and conquer, right? And then you could like recurse back up. Could you do that? Or like DFS down and up? If you considered each that's kind of weird. No, I don't know. If you considered each vertex to be... Oops. If you considered each vertex to be each ending index, I think you would get a tree. Sure. All right, hopefully that's pinned. I think you would get a tree, right? Some people hop in and they have no idea what's going on. Probably... I mean, I guess this is building a dominator tree. That's like almost exactly what that means, right? Computer science, a node D of a control flow graph dominates a node N if every path from the entry node N must go through D. Notationally, this is written as D dom N. Sometimes D implies N. By definition, every node dominates itself. Dominator tree. Dominator tree is a tree where each node's children are those nodes it immediately dominates. I don't know if I want to go down that route. I don't know if that's needed, but I guess I can pack that away. The idea being that like, if you could constrain your X and Y space, given some like subtree where you're like, if I'm here, then everything here has to go through me. But like my parent would be this, where like everything here has to go through me. Then you get some, the subtree would correspond to all of the vertices that, maybe that's the right way to do it. Because then you would get a subtree that corresponds to all of the vertices that are dominated by the root of that subtree. And then you would say, for this tree, I have this weird quality I want to figure out. Where I'm asking how many dx in the tree have a given, how many pairs of x and y are there such that dx is greater than dy, or like x is greater than y? How many pairs of values are there? Is that really simple though? The number of x and y values where dx is greater than dy? And then you would just DFS through the tree. You would say, keep track of the intervals of all values. That's kind of, yeah. It's kind of weird. You would need like a counter, but maybe. I don't know. Excuse me. So you'd say for this vertex, you could go to this vertex, which then dominates all of this, right? And then you would go to this vertex, and then this vertex, and then this vertex, and then this vertex, and then this one, and so on. And like if you're here, you'd say this dominates all of this. And then when you go to here, you'd say this dominates just this. And then you'd go through, you'd go to this, which just dominates itself. And then you go to here and you'd say this dominates all this. And then here, which just dominates this, or just this. So you could DFS through the tree. And then at each state, you could manipulate it somehow so that you're only looking at, or I don't even know if you want to do a DFS. You could do some kind of like weird divide and conquer, but yeah, you could DFS. It could be like DP. Could it? Yeah. Yeah, you could maintain like a sorted list of all the values. And then you'd say, for any given subtree, let's take like this subtree, you'd say, I have a number of distances to the end that must go through this vertex. How many of them can I just stop here at? This isn't really doing an inclusion-exclusion thing anymore. This is doing like you're actually building it up. So you'd say, like, if I'm looking just here, I have these two vertices I care about. So like there's exactly one combination where I just stop right here. Or I guess maybe two. Can they start on the same? No, they can't. So you'd say for this subtree, like res plus equals 1. And then you would go up and you would say for this subtree, I calculated the answer to this subtree. I calculated the answer to this subtree. Now I need to combine them, because the only world where you didn't stop either at here or here, like the immediate dominated children, are if you're going to stop here. So then you would combine them and you would say, but you could have many different things pointing to the same vertex, if I'm not mistaken. Yeah. So you could have many children pointing to the same dominator? How does that work? Because you need to like combine them. So we have that subtree and this root. And then res plus equals what? I think you could go subtree by subtree and say, these are possibilities for where X or Y begins. These are possibilities for where X or Y begins. So reconcile them. And then go, and then continue, and then combine them. So I think if I'm like moving away from this into the dominator tree world, you're saying you get the dominator and the children. So I think you could do like a union by size thing where you say, start with the first child. You're going to have some list of distances. That initially is DI. And then I understand what this means, but it's not that clear. Just like swap it so that like this one's bigger or this one's bigger or whatever. It doesn't really matter anymore. And then, or we'll call this DY list. So swap dx and dy. Bisect dx for each dy. Add dy to dx. Okay. Okay. All right, I think that's actually a working solution. So you build a dominator tree, and then you're kind of doing DP on the tree. It's not really DP. You're just DFSing through the tree. You're constraining like what subsection of indices you're looking at. And then you're returning up a list of all of the values in that subsection. And then you're combining them. And then you're joining by size. So creating the tree, I'm going to guess it's like O of, I don't know, O of N. Dominance. Blah, 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 blah. Let's see. Complexity. All right, great. So n log n, that's fine. But then there's no guarantee it's height balanced. But that's fine, because then you do a DFS. And then this should be O of n log squared n. Maintain a set, join it by size. Okay, I think that's it. I think that's donezo's. Hi. want to implement it, but I gotta take my dog out. I wonder if that's even close to. I think I'm at a stop. I have to stop myself, and I think my way of stopping myself is by looking at the hints and seeing if I'm at all on the right path. Jerry and Tom, hint 1. What's the optimal strategy? If you've obtained a formula for f of x and y, how do you calculate the required sum efficiently, perhaps by using some tree techniques? If d of x is less than d of y, Tom will never catch Jerry before... Okay, yep. Otherwise, Tom can move to the lowest common ancestor of x and y. Yeah. Okay. The first sum can be calculated by sorting the depth array. The second sum can be calculated by pre-computing subtree sizes. Let the size of the subtree u be S of u. The number of pairs of vertices with LCA equals u is equal to where v and w are children of u, S of v times S of w. Let the subtree size of u be S of u. Okay, yeah, this seems almost exactly like what I came up with, if I'm reading it right. I think they didn't call it a dominator tree, but... Is there any... Well, I think there's one more missing piece, which is... No, there's not one more missing piece. I already accounted for if Jerry drags his feet. This seems like it's doing it in a slightly smarter way. So the number of pairs of vertices where LCA is equal to u is equal to the sum for VU in children of u, okay, is equal to this. So they do it slightly, I guess, smarter than me, but it doesn't really matter because it comes out to the same answer. This part's kind of smart algebra, but I think my way works just fine too. So they're saying the number of pairs that have the given vertexes in LCA. Yeah, I think mine reduces to the same thing. In fact, I think you could just do this in O of n log n. I don't think you even need the O of n squared log n. Right? Why does theirs have that? second sum can be calculated by pre-computing subtree size of the third sum can be calculated similarly by separating the two components. There are many ways to optimize this process. Oh, wait, this is, yeah. Uses DSU on the tree. Okay, yeah, that was almost like mine. That's a cool problem. I'm gonna try to code this out later. I guess I feel like my dog kind of chilled out. I'm gonna try to do the weekly virtual. There we go. Longest alternating subarray after removing at most one element. If we compare adjacent elements in the subarray, then the comparisons alternate between strictly greater, strictly smaller. You can remove at most one element. Okay, that doesn't seem that bad. Integer n, an integer is called monobit if all bits in its binary representation are the same. The count of monobit integers. Excuse me. Okay, 0 and 1. That's good. 0, 1, and 3. So it's just the number of elements. Okay. I feel like the fastest way to type this out is for bit in range 32, x equals 1 to the bit, inclusive. We're going to include 0 in that. Okay, that's a pretty sloppy way to do it, but 3, 4. What's going on here? I guess this includes 0. So 0, 1, 3, 7. And then it said 7 break. And then there it said a 3 break. Okay. Final element after subarray deletions. Current player chooses subarray nums from L to R such that R plus L minus R minus L plus 1 is less than M, so a subarray of size at most M, where M is the current length of the array. Okay. The selected subarray is removed and the remaining elements are concatenated to form the new array. The game continues while one element remains. Alice aims to maximize the final element while Bob aims to minimize it. Assuming both players play optimally, return the value of the final remaining element. Interesting. Is it just going to be the minimum of these two? Yeah. Why would it not be that? Any subarray. The selected subarray is removed and the remaining elements are concatenated to form the new array. The game continues until only one element remains. Alice goes first and is trying to maximize it. So you could say try to hope for the 5, but there's only 2 options, right? If you have this, Alice can either say remove everything here and then immediately the game is over, you get x0, or remove everything on the other side immediately, you get the final x. Or the only reason you wouldn't do that is if there's something larger than those. But if there is, then Bob would just delete it. And the only reason Bob wouldn't just leave you with this is if there was something smaller than this. So I don't think it's worth tangoing. I think you just take the maximum of the beginning and the end. which works for these two, but that's fairly obvious. One, two, three, two, one, which would be the case, right? Because assuming Alice was trying to do anything else, she would say, okay, try this, and then Bob would say, no, you're sticking with the 1. What if it's like 1, 2, 3, 1, 2, 3? So in this world, Alice would, there's no reason not to do that. Okay, well, let's make it a little more complicated. 1, 4, 5, 1, 2, 3. Let's do like 2, 4, 5, 1, 2, 3. What about... I don't see any way. I mean, I really don't want to eat a wrong answer without having like proven this to myself, but if there's some smaller element here, if Alice doesn't immediately make it so that the 3 is the only thing left, then Bob can always just say you get a 2. Right? So that means at best, Alice will either get the 2 or the 3. So Alice just wants to take the best one. Okay, good. Ride sharing system. Okay, initializes the system, adds a new rider with rider ID, adds a new driver with driver ID, matches the earliest available driver with the earliest waiting rider, and removes both of them from the system, returns an integer array of size 2 where result is their IDs, or -1, -1, cancels the ride request of the rider with the given rider ID if the rider exists and has not yet been matched. Okay. Well, you put them into a set and a queue, right? Hi. Good boy. Give me 15 more minutes, okay? Good boy. 15 more minutes and then we'll go outside, okay? Good boy. We'll go outside, but you go lay down right now, okay? You go lay down. We got the set and the deck. Add rider. Is there any world where the rider is already there? Each rider ID is unique among riders and is added at most once. No, I guess not. Okay. Shit, that's backwards. Add a rider. So s.add x, q.append x. Looks good. Add a driver. Okay, fine. I guess I need set 1 and q1. That's fine. Really lazy, but set 1.add x, q1.append x. While, let's see, earliest available driver with the earliest waiting rider, and removes both of them from the system, returns an integer array of size 2. So while q and q at 0. Is that how you do it? Is this like O of n? I think it's O of n when it's like not near the end. I think it's kind of smart enough to know. Okay, well, while q and it doesn't really matter. While q, let's say x equals q dot pop left. If x in S, break. So I'm saying keep getting rid of things from the queue as long as they don't exist. And then the moment that they do exist, then break. If, let's see. And I think I want to do that too. So I'm saying like, or else you still didn't come up with anything. That way, if you pop through a bunch of empty elements, like non-existent writers, how long have you been doing Leetcode? Like 4 years now, maybe 5 years. Yeah, this makes sense to me. Okay. Can the driver cancel? I don't think so. So if not Q1, return -1, -1. It's not possible. If x equals -1, return -1, -1. Y equals Q1 dot pop left, return yx. And then I guess I also want to say like s1 dot remove y. Is it remove? Whatever, I'll find out. Cancel writer, that should just be s dot remove the writer ID. Okay, fine. Null, 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 2, 3, 5, 1, -1, -1. 8, 8, -1, -1. I guess I'll go through this one more time because I didn't really think about this that hard. So we've got the current writers that exist, the queue of writers that exist, the current drivers that exist, and the queue of drivers that exist. So if you're adding a writer, designate that they exist and add them to the queue. If you're adding a driver, designate that they exist and add them to that queue. Okay, if you're trying to match a driver with a writer, if there's no drivers, immediately return, or else you're looking for a real writer that exists. So maybe there's no writer that exists. While there's any potential writers that exist, pop them from the queue. If they do exist, then you found one, or else go back to it doesn't exist. If you didn't find any and you emptied the whole queue, then there's no writers. Or else get the longest waiting driver, designate that they don't exist, and return them. That seems good. Longest alternating subarray after moving most one element. Subarray nums from L to R is alternating if one of the following holds. Nums at L is less than nums at L plus 1 is greater than nums at L plus 2, or the opposite. You can remove at most one element from nums. Then you select an alternating subarray from nums. So this seems like a sliding window thing, right? All right, I don't even... Yeah, this seems kind of like a sliding window thing. I guess you could say for each index, if you started... There's two things that could happen. You either say this is less than the next thing and greater than the next thing. Let me think about that. A subarray is alternating if one of the following holds. Yeah, but you don't get to make a choice. Either one holds or the other holds. Right? So you're going to get a bunch of disconnected subarrays. Yeah. So if this is your array, if this is like the height map, you're going to get a bunch of these. And I think all you care about is this greater or less than, like for each pivot. So then you're going to say, okay, there's all these little separate components. And I guess you just get to add two of them together if you want, right? You could say, okay, well, fine, then delete this. No, because this could still be like, it would go down, 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 up, right? But you could just check that. You could just say, if I deleted this, does it work? If I deleted this, does it work? because you're only ever going to delete something at an endpoint, and you're only going to delete something at an endpoint to make both of these be contiguous. There's no reason to do anything else, if I'm reading this right. Yeah. So I'll just say A is equal to this, and this is going to have the left val, the right val, and the length. For x in nums, let's see. Cur is that. Yeah, that's fine. If not cur, if current is empty, I don't even think I need to say that. I think I can say if. Is this right? Does this hold? Is this the only reason why you would ever remove an element, is to combine two adjacent subarrays? Because if so, then this works. But I worry there's some weird thing that would happen where actually you're going to get this, but that doesn't really make any sense. Because like this element will always be less than this element, and this element will always be greater than this element. Like you can't really change that. You get to change it at most once, but the only time you would ever want to change that is at the end, between two elements that aren't following the pattern. Is there any counterexample? Are the examples any good on this? 2, 1, 3, 2. So you don't have to do anything. 3, 2, 1, 2, 3, 2, 1. So I guess you get rid of 1, 2, 3, 2, 1. You get rid of the 2. And then you could have 2, 1, 3, 2. That's pretty good, I guess. Okay. No, you could still have some weird stuff going on though. Because you could have like this subarray, and then a subarray of length 1, and then this subarray. And you definitely, like, there's a world where you would want to like get rid of this, and then these connect. So I think I'm like honestly kind of overthinking it a little bit. I think I just need a prefix and a suffix. So given a certain element, how far forward can you go? And given a certain element, how far backward can you go? And then you would say, okay, there's two options. Either one, I don't delete anything, in which case it's going to be prefix plus suffix for every x and y that works, or prefix plus suffix for every x and y that's one apart that works. Okay, that's fine. This was too convoluted anyway. Prefix is 0 times n. Suffix is 0 times n for ix and enumerate a. I guess these are really 1 times n. So x is a at I. So start here and say, how far backwards can you go? If x is, let's see, how does this work? If x is greater than, I'm going to say y is a at I minus 1. If x is greater than y, then you do something, or else something else happens. Do I need 2 prefixes and 2 suffixes? Is that smart? You're saying the prefix if you're zagging or if you're zigging, or the suffix if you're zigging or zagging? I don't think you need that, because if you know one of them, the other one's always going to be 1. But I think I am going to do it that way. Okay, if x is greater than y, let's start with if x is less than y. If x is less than y, because that's what all the examples are, then okay, P1 is go down to the left, P2 is go up to the left. I'm going to swap these, I guess. This is confusingly written. So this is the thing previous is greater. So if you're here, the previous thing is greater. So P1 at x is equal to P2 at y plus 1. P2 at x is equal to 1. Right? You're saying, and if you tried to go left and have it be smaller, then you're fucked. Okay, and then this is just vice versa. So P2 at x is equal to P1 at I need to be careful. This is not x and y. I don't know what I'm doing. P1 at I is equal to 1. Okay, so this should handle the prefix, and then it's just the suffix. So for I in range n minus 2 minus 1 minus 1, x is a at I. It's going to be really similar to this. This is now a at I plus 1. This is plus 1, plus 1. Okay. And now suffix 1 is if it's less than the next thing, right? If x is less than y, then suffix 1 and suffix 2 become what they are. And suffix 2 is if it's greater than the next thing. And now it should be pretty simple. So res is 0. Return res for I in range n minus 1. This is if they're valid. So x equals a at I, y equals a at I plus 1, right? So you're saying take each pairwise thing, try those. So if x is less than y, this is the world where you're saying, like, what's an example? Right here. Then you want x to be greater than the thing before it, and y to be less than the thing after it. So res equals max res and greater than the thing before it, less than the thing after it. So P2 and S1. P2 at I plus S1 at I plus 1, else P1 and S2, which should be x is greater than y, so you want to go, no, I think I have this backwards. If x is less than y, yeah, then it needs to be greater than its previous thing, and y needs to be less than its next thing. Or else it's greater than y. Actually, I need to be careful because I'm guessing, yeah, it's like strict greater than, less than. Else S1 at I equals 1. S2 at I need to count for the equality too. X is greater than y. Else P1 at I equals 1, P2 at I equals 1. Okay. res, I guess, can always be 1, right? No, actually, there's no else here. Okay, if x is less than y, you went down to get to the next element. So you want to go down to get to the previous and up to get to the one after the next. Yes. Or else you went up to get to the next element. I'm fairly certain I have these backwards. If x is less than y, no, this is right. And it's also going to come to bear pretty quickly. Okay, so that's that. For I in range n minus 2, and then it's going to be exactly the same thing, but what if you removed the element in between? So now this is I plus 2, I plus 2. And that should be it. We got 2, not a good start. 4, 1. 4, 4, 1. So what happened here? Res is 2. I think what happened is, no, it should be 4 a bunch of times. It should say, like, if you took 1 and 3, you'll get 4. It's, like, redundant, but it shouldn't really matter. I guess I'll print P1 and P2. So we should see, yeah, 1, 2, 3, 4. So it should say, and then if we did like S1 and S2, it should be kind of that, but backwards, right? Yeah, 1, 2, 3, 4. So if we chose any of these, it should be like 2 plus 2 or 3 plus 1. Not there, 3 plus 1. So why would it not do that? For I in range n minus 1, we get x and y. Oh, did I change the values? 2, 1, 3, 2? No. What are these actually coming up with? So it tried one thing. It said compare 1 and 3, which is weird. I don't think I defined n anywhere. Oh, no, that's not that weird. That's because this is the only, so it's saying 1 and 3. So this is the only time where you're going up from x to y. But it should say P2 at I. Maybe I have these backwards. Yeah, I do have these backwards. Okay, last time double checking this. So now it should say 2, 2. Perfect. So P1 at I is, if it's less than the thing before it, then that's like an actual number that's not just 1. P2 at I is if it's greater than the thing before it. So then this is saying if x is less than y, it also needs to be less than the thing before it. Okay. 4, 4, 1. Let's see how it does. Nice. That was pretty speedy. That was pretty fast. That was within half an hour. could have done better. I wasted a minute on Q3. I wasted a minute on Q3 double checking. I literally wasted like a minute or two just being like, does this all look good, and looking through the code again. I wasted a long time on Q4 as well. What happened here? I came up with something like decently quickly, but that wasn't, I don't know, not the fastest. I didn't really come up with the solution very quickly. I think it's really nice for me though, because I didn't really want to like lose sleep over like not being rigorous enough. You're gonna do the weekly later? I don't know. Maybe I'll peek and skip, but I don't know. I already have done, what's this, 4 hours of just straight Leetcode and Codeforces. This is your first contest. That's cool. Have you been practicing a lot of like the actual like Leetcode problems? I think I did like a lot of Leetcode problems before I ever did a contest. I think I also got really confused about like this. I even left a comment for myself, but I was questioning it so much. And I guess I was right to, but I feel like I spent so much time thinking about that again. And I almost would have been better off being less rigorous about it, because at the end of the day, like what happened anyway, where I got it wrong. And like it's a simple enough thing, you either get it exactly right or you get it exactly wrong. So it didn't really matter to like constantly double check all of them all the time. Happy if I get 2. Yeah, that's a good place to start. I'm trying to shoot for 2 or 3. I don't know. They're harder these days, so. I would have finished just above JavaScript guy. Which is crazy. In Go, what the hell? I wonder what's the error people were missing on this one. What's up, Vortism? Did I do @coder? No. I can take a look for like 2 minutes if there's an interesting problem, but I'm just about to hop off here. Yeah. All right, well, it's a good stream. I guess sometimes I like to like review, like what did I do that was of interest? What was interesting? This was pretty interesting. This Codeforces problem that Solaris sent me. This was like, I feel kind of proud. I like got this one. I didn't implement it because I don't feel like I have time, but it was kind of like build a dominator tree and then DFS through it. I think calling it a dominator tree is a little bit weird because like the conceit of the problem is like the way they formulate the graph means like that's like a little bit overkill, but that was kind of cool. It was pretty satisfying to like come up with this solution. And I think even past the dominator tree thing, like even if you just called it a tree, it was still kind of overkill. Because I think the idea is you're kind of like combining children of a given node, which my my solution did, but there was this fucking problem, which as far as I can tell is Knuth optimization, which I've literally never seen. I've seen that exactly once in an @coder contest, but I've never seen that in Leetcode. So this is LLMs the problem, I guess. Oops, all LLMs. And then that contest I just did. I don't really know what's to be gained from thinking about this. Was there an interesting problem before this on this contest? Kinda. Not really. Oh, this was the big thing. This was the big thing, like, why did this not work? So far as I can tell, there's a Venn diagram, not a Venn diagram, but there's kind of 3 things that you can use. As far as this problem goes, there's Knuth optimization, which I think almost like no one's heard of. There's the alien trick, where you kind of say like, okay, if I have some DP at I at j, and that's going to be equal to some like f of I and j, I don't know, given some constant values like k and n and stuff like that, I'm just going to like make my own value lambda, and then I'm going to binary search for the optimal lambda. That's very confusing to me, but again, with the biweekly Q4, I don't know, man. I'm trying to think about like what's to be gained, what's to be learned from this, right? And then there's the convex hull trick, which is like dp at I is equal to f of dp at j. Such that f is affine. And this made sense to me. I feel like this is what I tried and it didn't work. And it seems like it's just a hard implementation problem where you have to know some obscure tricks that won't ever appear in less than 2600 rated ELO Codeforces problems. Yeah, I mean, I'm not trying to shit on the problem. I guess it sounds like I'm trying to shit on the problem. Maybe I am, but like, I don't mean to. It is actually a pretty interesting problem. It's just, I'm surprised that there's like 3 separate DP optimization tricks that all kind of seem like they show up here. And when we went through like multiple different solutions for this, none of them made any sense. Like they were all clearly generated by an LLM, and the actual code itself was like really confusing. I don't know. In my mind, it's like kind of worth puzzling about that, I guess. The tricks in Tom and Jerry. I don't know if you were listening to me when I was solving that one, Solaris. Is dominator tree the right term for that? Is that the right? That's what I like read the editorial after, and I was like, that seems almost exactly like what they came up with. I didn't end up coding it out, but I ended up like doing it and then being like, I don't want to spend the next hour like implementing a dominator tree thing, but I looked at their solution and it was almost exactly mine. How would I describe Knuth optimization? So that's the alien trick. That's the convex hull trick. This is not a very good description of the alien trick, but whatever. Knuth optimization is f of L and R is equal to some f of k, L and k, plus f of k plus 1 and R, or let's say k and R, plus a cost from L to R, and f of okay, it's the quadrangle inequality. So it's the cost of A to D plus the cost from B to C is greater than or equal to the cost from A to C plus the cost from B to D, where A is less than B is less than C is less than D. I didn't use a dominator tree. Oh, really? I mean, maybe I'm using that term wrong, but yeah, I guess I kind of thought like you're, the way I thought about it was you're artificially constraining it to say, what if I stopped at a given index? What are all the X and Y values where it's valid to do that? And that's going to be all the X and Y values that are dominated by that node, Z, where you could start at some Y, just go to Z, and then stop. So it's like the LCA kind of. But I think the fact that they say this kind of means that a tree representing the graph is a little bit the same thing as a dominator tree representing the graph. What was your approach? Okay, but anyway, there's the quadrangle inequality, which then results in a certain convexity. And I think the right way to write this is to say convexity in f of L to R with regard to R. So it's always optimal for both players to jump the most to the right, hence the DAG is reduced to a tree. Yeah. The parent is the rightmost of the node. I guess, yeah. Like, actually, now that I think about it, I see where you're going with that. I think a really useful thing to streamline it too, and maybe this is what you're about to say, is like if there were some x comma y where x wins, then that means that there was some y comma x where y won. So therefore, when you're looking at children and you're looking at the LCA, you actually don't need to keep track of, like, for some node down here, you don't need to keep track of like these things relation to each other. You just need to know, like, okay, well, this works and this, like this pairing works exactly if one of them comes before the other. Or like that pairing works in exactly one order. For each pair x and y, Tom wins if depth at x is less than or equal to depth at y, and it scores the distance from x to LCA of x and y. All right, my dog really wants to go out. Yeah, that makes sense though. That was an interesting problem. I saw a lot of people rate it highly. All right, well now I'm outie for real. See ya.